joining with us at 11:30 or 45 minutes at that time. So we can start our inaugural session. Inaugural session, we can start, sir.
Kindly start.
We are today's we will be having for 5 days faculty development program, and this program will be for the scope, for having the scope and opportunities of VLSI design using cadence tool and the Entable technology, who are the Indian university support vendor for this tool, for using this tool. So they will be supporting us with the hands-on and workshop session. So in this way, we will be really learning a series of program so that we can learn the VLSI design flow. So for this FDP session, 5 days FDP session will be inaugurated by our Honorable Vice Chancellor, sir. And sir is very much fascinated with VLSI chip design, and sir told many of the times that if we can start our tool design for VLSI chip. So sir, we have initiated that theme, and hope we'll be starting soon this your dream.
Thank you, Dr. Madhumita Daswarkar. So it's nice that your department and under the leadership of you as Professor Sinha, you are organizing these faculty development programs on a very important topic and this is relevant, very much relevant in the current context. This chip design technology that is relevant in that sense because of the changing scenario of geopolitics. In India, what we are observing, a large numbers of organizations who were earlier not so interested in investing in India, they are coming to India for a huge investment in near future. And this is the reality when within a few years, we will be seeing a large numbers of organizations are working here for chip development, for hardware development, and so on. And this for the last these 2-3 decades, we developed the culture of giving more focus on service-based these activities, and more reliance on softwares, more reliance on services, and all these things, and mostly, and that has become one of our major thrust area. And for that part, and in doing that, we have neglected this hardware development and a focused approach on this hardware development activities, entrepreneurship, business in this country in the last few decades. And this is the time to make a change. And because whatever we are observing, all the devices which are, this most, the major part of it, all the devices, digital devices, gadgets, and all these things, which are available in the market, in Indian market, major part of it are from, these multinational organizations with a production base at other countries. And that is this one of the weakness in our this Indian economy, Indian technology. And here this is the time to take an introspection, and therefore we need to have more focus on this hardware based technology, chip designs, fabrication shop, the semiconductor devices, and that is going to be of very important in the business scenario, and that will create a lot of opportunities for our engineering students. From my personal experience, what I can say in the last this 10-15 years or 20 years, the engineering students this is the outcome of the culture. They are more focused on us to this to work this in service and softwares and all these things. Now, and on this training in this area will give them the real insight. And as the future is moving in that direction, so this is through these faculty development programs, all the participants, all the faculties who will be joining here, they this will be in a position to convey the importance of this chip design technology, fabrication, this semiconductor fabrications, and all this hardware related technology to the students, and encouraging them to develop a career in that direction. And we need a large number of professionals. We need a large number of technologists, engineers in this field for more innovation, for more new generation of new ideas and new technologies from this country. And this is the thrust of this government also. So now this academic institute like us, we should take a pioneering role in this propagating this culture, in this knowledge, in our learning community for this future outcome in the form of a skilled generation of skilled set of skilled manpowers, knowledgeable manpowers, technologists, engineers, design experts, and all them for taking up the challenges of the future. So I wish all the best for this faculty development programs. I wish that all the participants, they will be benefited, and whatever they will be learning from here, that will have significant importance for their these future endeavors. But at the same time, there is no end of knowledge, and if they want to upgrade them further, so my request to all of them is kindly browse these digital platforms, internets, and acquire more knowledge, more information in this area. We will be organizing some more programs like that in near future. Try to join these programs as well. And my sincerest thanks to the resource persons, to all these these experts who have kindly consented to share their knowledge and experience with the participants present over here. My thanks to Professor Amitabh Sinha, Dr. Mundumukta Dasharkar again for organizing this. And my request to them is kindly, to organize in a fruitful manner for the next coming 5 days, so that there is a there should be a level of this the testing to assess the level of understanding of all the participants. And if there are certain queries, confusions, these new ideas, new opinions, kindly take a note of all these things. We have created our discussion forum, so try to use it as effectively as possible. And with this, I'd like to conclude, and I am requesting Dr. Mundumukta Dasharkar, Professor Amitabh Sinha to take this session away further for the benefit of our learning community. Thank you.
Yes, sir. Thank you so much, sir. Yes, if we are getting your blessings all the way, we'll be able to take forward this kind of initiative in future also. And I think that in Eastern region, we'll be trying to grow a skill manpower so that really we can contribute something in national movement of Make India or this kind of program, even in SMDP program also. So thank you, sir. Thank you for giving us illuminating and motivational talk about this event. So now we can start our inaugural talk, others by our, our director, Professor Dashgupta, Professor S. Dashgupta, Shivamay Dashgupta, our honorable and our respected director, sir. If you say something about our FDP program, we'll be really motivated to start this session. And we think that your blessings and your motivation will lead to us a very grand success of our events. So please, Professor Dashgupta, if you can join. Sir has come. Prem?
No, ma'am. Ma'am.
Yes.
Sir,
Mir, you
I
can now.
Maybe some network problems that did not. Yeah.
Sir is busy with some work.
Okay. Yes, I think so. Sir didn't till now. He did not get the connection, I think. So we can take forward if you permit.
Okay. So next, Professor Dr. Giri, Devashish Giri, who are a techie coordinator and supported a lot for organizing this seminar. And he is the instrumental part. He has supported the instrumental part of this seminar. So please, Dr. Giri, if you come and say something about this FDP program.
Ma'am, Giri sir was not able to join due to some.
Okay.
No,
So
I can see that except Dr. Amitabh Sinha and Anand one is available. Kindly request Dr. Amitabh Sinha to express his views, and after that, you invite the resource persons for presenting their these ideas and experiences for the participants.
Sir, actually, the group head of Semiconductor Industries Limited, Government of India, he will be joining with us for enlighten us for some illuminating talk so that we can step forward towards the SMDP program or any national program in analog VLSI as well as digital VLSI design. So he will be joining probably 11:30. So up to that, if sir, if we keep your valuable time is there. So if you with us, then I think it will be a great event.
I have to leave. I have another program at 11:30. So kindly,
Okay.
the Dr. Sinha is there. Professor Sinha will look into it. Okay. The
Okay.
entire.
Then when you will be joining, after that, I will be again we can communicate with you so that you can come and.
No, let's start, Madhumita.
Let's
Okay,
start.
sir.
Let's start.
Start, you know.
Okay. Okay, sir. Thank you. Then we can start the keynote session. That what are the outcome we will be getting from this FDP session, and what is our motivative and what is the challenges and opportunities still there in the VLSI design, in research, in industry, and in academia, in everywhere. So the student should know about it, how they can start, how they can motivate it out of this session. So please, Professor Sinha, you, if you can give some illuminated notes about this FDP.
Thank you, Dr. Madhumita Sharkar. Well, Honorable Vice Chancellor, respected panelists, dignitaries, and respected audience. At the beginning, I would like to convey my gratitude to our Honorable Vice Chancellor, Professor Sharkar Moitra, for his excellent inspirations. Very rightly, in fact, he pointed out that certain things are very important. One is the technology development or VLSI technology. We have to develop the human resources, his test on that, through innovations. And another thing, he encouraged, for the development of chip. So chip design, fabrications, his taste on all these very, very important issues. In fact, today, we are going to discuss on this. In fact, over the few days, we'll be discussing on the analog design and development in industry, the scopes and opportunities. So it is my great privilege to get an opportunity to say a few words on scope and opportunity on analog VLSI design in industry on this faculty development program. Eminent personalities will deliver talks on different aspects of analog VLSI design over the next few days. So we'll get opportunity to hear from them. I would like to mention one thing, regarding the advent of analog VLSI and mixed signal circuits. How this development of analog circuits have made it possible to emerge a wide range in applications. To talk about analog circuits and their importance, I would like to mention the widely accepted article published in Red Herring magazine from California in February 2003, just 17 years back. It was mentioned that analog chips enable computers to interact with physical world, to see, listen, and touch. And another interesting line which was mentioned there, the next 10 years we'll see a shift in emphasis to analog technologies. In the coming years, look for analog, not digital chips to attract the new talent and investment. Now, whether the global talents have totally been shifted towards analog, not digital, may be a debatable issue. But it is true that huge amount of investment has been made globally on analog circuit manufacturing, and it is definitely true that analog circuit design and applications have occupied an important role in VLSI design. And it's also a matter of fact that mixed signal ICs, which leverages both analog and digital circuits to meet emerging applications, starting from low-end applications to high-end, and they're becoming attractive for VLSI chip for the system designer. Now, one thing, when we talk about these mixed signals, that means the importance of analog circuits is quite evident from that. Another article which was published in February 2004, Texas Instruments, the leading semiconductor giant, they also predicted that DSP and high-performance analog devices are the engines. And we are only at the beginning of where analog is going. That's a very interesting statement. So today, if we see the advancement and the importance of analog circuits, and especially mixed signal circuits and systems, it is amazing. Now, before going into mixed signal circuits and application, let's have a look at the historical evolution of analog circuits. Now, these historical evolutions, if you understand that, this will help us to understand and appreciate the progress of analog circuits. The metal oxide semiconductor, the field effect transistor, commonly known as MOSFET or MOS transistor, was invented at Bell Labs in 1959. And this MOS integrated circuit chip was proposed soon after. But MOS technology was initially overlooked by Bell Labs because Bell Labs, they were more interested in communications, in telephone. So they didn't find it practical for analog telephone applications. Before it was commercially used by Fairchild and RCA. These are also the giants, semiconductor giants for digital electronics, such as computers. Now, MOS technology eventually became physical for telephone applications with the MOS mixed signal integrated circuits, which combines analog and digital signal processings on a single chip, developed by former Pale engineer David Hodges with Paul Gray at University of California at Berkeley in the year 1970s. In 74, Hodges and Gray worked with Ari Sural to develop MOS switched capacitor circuit technology. And MOS switched capacitor circuit technology is the key technology for mixed signal processing today. And ultimately, they developed digital to converter chip using MOS capacitors and MOSFET switches for data conversions. MOS analog to digital converters and DAC chips were also commercialized in 74. We understand the importance of analog to digital converter because real life signals are all in analog. For processing with the digital signal processor, a specialized microprocessor, we need to convert them into digital. Now, CMOS complementary PCM codec filter chip was developed in Bell Labs in 1980. So, in fact, all are the development which took place in these years, and ultimately we found that in 90s and all these analog circuits, along with the digital and the mixed signal processing circuits, became very, very popular, especially in telecommunications for switchings. And
Hello, hello, sir. Hello,
Hello.
hello, Madhumita ma'am. Hello, sir. Sorry to interrupt.
Hello.
Sigma sir has joined.
Yeah,
Sigma
okay.
Gupta sir has joined, and Girish has joined.
Okay. So, hello.
Yes, welcome,
Yes, sir,
Dr.
sir.
Giri and
Let
Professor
Professor
Dashgupta.
Sina Madhumita, let Professor Sina continue with that.
Okay.
So, another important applications of analog VLSI are the RF CMOS circuits. So, in early 1980s, in Bell Lab research work on the development of submicron MOSFET VLSI technology was going on at the Advanced LSI Development Lab, and designs at the lab demonstrated the potential in MOS integrated circuit technology. Today we see the importance of RF circuitry for devices, communication devices, especially this in mobile handsets and all. So mixed signal processing, knowing the brief history of evolutions of invention of analog circuitry, if we look at the mixed signal products, we may observe that they are rarely created entirely in the analog or digital domain. These days, many of improved applications are now made possible due to the innovation of integrations of firmware running on DSPs or micros with analog or mixed signal analog circuit contents. In fact, this firmware is very important. This is the software for a particular applications has been converted to bits and are stored permanently in the chip. So, understanding the importance of this firmware, digital and analog circuitry, we have to understand the complexity also. The magnitude of complexity is also very important, is understanding how to deal with it. Firmware systems have many more elements than analog designs, but more fewer than modern PC software in PC programs. Modularity and structured programming are vital for managing complexity. So in firmware, limited system resources can modularity very difficult, and less complexity makes it unnecessary. Another key areas to reduce complexity is following the naming conventions for functions and variables. This is a very important issue. Analog engineers can provide clear and consistent signal names, especially for signals that are connected to processor pins. The programmer can use the same names inside the program, making the integration between the program and signals perfectly clear, and this will be easier to understand. So it is clear that designing mixed signal systems, analog and digital designers need to come more closer by adopting some common concepts. Another important areas is test and measurement. These are also very important. In fact, for digital systems, there are many tools available, like in-circuit emulator, in most commonly used for software debugging. But as such, for analog, the still in fact, the tools are limited to oscilloscopes or wave analyzer or this kind of tools. So here also, in fact, a lot of work is going on for making the testing simpler. Testing tools are already there for analog. It's not that these are not there. But now the most important thing is worldwide, the development time should be reduced. Now, development time should be reduced, and for that, this debugging is also a very, very important factor. So, for the digital system designers, many things have been standardized, which is yet to be done for this analog systems. So, a lot of work is going on in that aspect also. So, these different techniques are indispensable in the design of mixed signal systems, and analog and firmware engineers spend more time for that. Now, another thing is that simultaneous and sequential. In fact, in digital system, the processors, they work on the sequential fashions, whereas in analog circuitry, the whole circuitry can be made in the parallels. Even though today some field programmable digital array, like field programmable gate arrays, which are digital circuits, they perform parallelly. But mostly, in fact, we use the digital processor for personal computers to signal processing applications, to many microcontroller applications. So they work primarily on the sequential basis. Now, most mixed signal ICs often used for converting continuous time analog signals to digital signals so that digital devices can process them. This is done by well-known concept of sampling, quantizing, and coding processes. Sampling process employs MOS analog circuit to convert continuous analog to discrete analog circuit, and is basically an analog circuitry. Quantizations and coding, basically, in fact, they are the combinations of analog circuitries and digital circuitries. Mixed signal ICs are essentially components for FM tuners in digital programs, such as media players, reshape digital amplifiers. Any analog signal, such as FM radio transmissions, a light wave for sound, can be digitized using the basic analog to digital converter. So mixed signal ICs are difficult to design and manufacture than analog only or digital only integrated circuits. So apart from ADCs, examples of mixed signal integrated circuits include data converters using sigma delta modulations, digital to analog converters, etc. So to talk about novelty and importance of analog circuits, we have been discussing on mixed signal circuits. However, in recent times, a new branch of analog electronics has been emerged as reconfigurable analog circuits. The concept of reconfiguration of analog circuits has been known and used since the inception of electronics. To understand it, take the example of our old radio receiver system. To switch from medium wave to short wave to short tube was accomplished by rotating a mechanical switch, which in turn configured to a required circuit. However, the universally configurable circuits called field programmable gate arrays have been developed over the last 2 decades. And here, the switch is done by electronic switch. So an analog signal can be viewed as a signal which has continuous values with respect to time. On the other hand, we have quantized signal which may have only discrete values in the time domain. Among signals can be divided into classes. Anyway, without going into the detailing, we can understand the reconfigurable analog circuits, or commonly known as FPA, consist of analog circuits like capacitance, operational amplifier, digital circuits like counter, controller, memory, switches. So FPAs are also example of mixed signal circuits. So finally, to conclude our discussion, we need to list down the challenges of mixed signal circuits also. It is known that CMOS technology is usually optimal for digital performance and scaling, while bipolar transistors are usually optimal for analog performance. Until recently, it has been difficult to combine them in a circuit in a cost-effective manner, or to design both analog and digital in a single technology without major performance degradations. The advent of technologies like high performance by CMOS, etc., have removed many of the compromises that previously had to make. So testing functional operations or mixed signal ICs remain complex, expensive, and often some kind of challenge on implementation task. Systematic design methodologies comparable to digital design methods are far more primitive in the analog and mixed signal area. Analog circuit design cannot generally be automated to nearly the extent that digital circuit design can combine. So, considering these aspects, combining the two technologies multiplies this complication. So that means when we are thinking of mixed signal processing circuitry, the complexity is the more. So first, changing digital signals and noise to sensitive analog signal inputs. That's also very important. One path for this noise is substrate coupling. A variety of techniques are used to attempt to block or cancel this noise coupling, such as fully differential amplifier or on-chip decoupling. So I'm sure that these issues may be addressed by the respected experts in this FDP program for the next few days. With this, I conclude. Thank you very much.
Thank you, sir. Thank you for your illuminating and the most important part of our program, that why we are going for this analog VLSI design and the mixed signal design, which are coming up with a huge impact in our ASIC design and other part of our design. So really, thank you, sir, for and you will be with us in continuing this type of FDP, so that this can be a great success. Thank you, sir. Mihir, now uh, we can have our director, sir. Mihir, yes.
Okay. Yeah. Thank you,
Hello.
ma'am. Right. Yes, ma'am. Thank you, ma'am. So,
Yes.
uh, so I would like to uh, invite our honorable director, sir, Professor Shiomoy Dasgupta, sir, to give us his motivational speech to us. And I would like to say something about sir. Sir,
It's all right.
uh,
Okay. Mihir, ঠিক আছে. Okay, fine.
okay,
Let me
okay,
start it because already for your inaugural program, the time is going up actually, you know. So,
okay,
okay.
okay, sir.
So I think I joined late, but Honorable Vice Chancellor sir must have given you motivational, you know, speech actually. He is always the prime mover of all these activities. And Professor Amitabh Sinha also has discussed a lot of things that, I mean, contextual issues. And I think VLSI is very important. And although in our India, we are designing VLSI, uh, I mean, chips and other things. And in fact, I remember in 80s when the Texas Instruments set up their R&D in Bangalore, and they had a collaboration with IISc Bangalore. And during that time itself, but unfortunately, the production or manufacturing of VLSI ICs or even any IC, that has not taken up. So in BEL, actually, Bharat Electronics Limited in Bangalore, they started their plant. That is a small plant. They made several ICs also. Few of them became very popular. But and then semiconductor complex in Chandigarh, in a big way they came up. But ultimately, still we could not do much. And so we have to depend on, even if we do design and all that, we have to depend on other countries for manufacturing and implementation. So what is that is a major shortcoming of our VLSI technology, teaching VLSI technology, because they cannot see, the students cannot see the plant, students cannot actually experience what are the intricacies in implementation. So that is one of the issues here. But of course, within the, I think, limitations, we can still progress, and conceptual aspects of VLSI that can be taken up. And I think that people from India, they are also contributing in a significant way. So that is very issues. And you know, now the design is already mostly computerized. And in fact, long back now, the this only thing is that application softwares have come up to common users level almost. So that is actually one advantage, that more and more people, more and more creative persons can, I think, take up the issues, and we can have better and better solutions. So, but it should be, to some extent related to, I think, while teaching by VLSI and other this subject, that should be translated to production, because you know the students, that is one of the major area where our students do not get much of exposure. And with the help of videos and other facilities, the computerization facilities, I think that can be to some extent compensated. So with this, I congratulate all the organizers and the head of the department of VLSI, the microelectronics and VLSI. See, this is actually, VLSI is very closely related to microelectronics. Now, microelectronics is another area where we need to have significant, development. And the microelectronics again has a link with physics. So that is another issue, because what is happening technologically, we are not that much progressing. Even say 2 decades, 3 decades back, where we are still further less now. And many countries like China and other countries actually have come up. And that production actually has gone mostly to Far East countries, and recently in China. So we should think of how this production of VLSI chips and other things we can take up, what actually is actually preventing us. Now, with that, I wish all the best for this program and congratulate Madhumita Madam for organizing within such a short time, and congratulate Devashish Giri sir for to fund it from TQI 3 program, and all the faculty members, and of course the participants. So I congratulate all the participants, whoever have actually registered and will go through this program, and request them that they should make the most of the, I mean, of this event. Okay, and I also extend my sincere thanks to the resource persons. I don't know today who will be the resource person, but there must be some resource persons. I heard from industry also that there may be some resource person. So all the resource persons, I extend my sincere gratitude, because in spite of their busy schedule, they have actually agreed to enlighten us with significant, information and their contribution. So with that, again, thank you all, and I wish a grand success of this program. Thank you.
Thank you, sir. Thank you very much for your inspirational words that will help us. And now I would like to invite Dr. Devashish Giri to say something. And as I say, as sir pointed out, uh, he is the TCUP coordinator. He is working currently as an associate professor in Department of Information Technology in Maulana Abul Kalam Azad University of Technology. His current research interest includes cryptography, information security, e-commerce security, and design and analysis of algorithms. So I would like to request Professor Giri to say something in this platform.
Thank you for introducing me, and very good morning to everybody, and honorable, respected, honorable Vice Chancellor sir, uh, honorable, respected other dignitaries present in the 5 days FDP program on VLSI design. I am very much thankful that Professor Professor Dasgupta sir and their team has organized such type of event in our institute, and Professor Madhumita Dasgupta also, he has supported to the many things for the students as well as the faculty community in our university. So already Professor Simamai sir, Professor Amitabh Sinha sir already discussed about the VLSI technology and design. VLSI is a process of creating and integrated circuits by combining thousands of transistors in a single chip. Earlier, VLSI design was the complex based on the semiconductor. Now, within 1 decade, there is huge change in the VLSI technologies due to the different interest in electronics industry, and it is having the many application in the computer science and electronics. For an example, say for high performance computing, we are using that VLSI design, and then for image and video processing, we are also using the VLSI design. Since my area of interest is cryptography, network security, and VLSI design is also very much applicable in the cryptography and network security to design the system so that we can efficiently compute the many things, and we can even see in the attack procedures. Many researchers are doing some work on the area of VLSI design so that they can easily they can efficiently attack the systems. So I congratulate the Madhumita Das Sarkar for organizing such type of faculty development program. I expect that workshop will be grand success, and thankful to the other organizing committee, and thankful to the speakers, those who will speak in this FDP program, and my dear students also. So in these few words, I conclude my speech.
Thank you.
Thank you, sir.
Thank you, Dr. Giri, for your presence over here. And really, it is your support from TechEve, without which maybe this kind of FDP cannot be possible. So thank you once again, as you are always giving us support for any kind of, this kind of leading activities. Thank you once again.
I'm having another event. That is what I will see.
Okay, okay. No problem.
It's going on there. Okay, thank you.
Thank you. So now we can start our keynote session. And yes, welcome, Mr. Chatana, for your presence. We are really happy that you are coming over here to grace the occasions, because we are here for starting an initiative towards the Make India and the SMDP program, because we have the MTech in microelectronics and VLSI technology, and our students have already contributed, contributed to different organization and research institute also in the field of microelectronics, as well as in the field of VLSI design. They have placed in Intel, Qualcomm, and several abroad research institute in different national research institute in abroad also. And most of the students are really, they are doing research in different national important institutes. But we are really very much concentrated earlier in the field of digital design, digital domain. And although we have the intention to have the process and the device domain, and also the characterization domain also. So really, as your presence and your illuminated talk, I think it will be leading towards our department and us towards a new step towards the Make India and Others government program. So thank you to welcome in our university and this FDP program. So now can we say something about before his talk, we can say something about the brief introduction of Professor Jatana. He is the group leader or in the semiconductor laboratories, which is a very important laboratory. And most of us in our early age was having a dream to go there and to see what is happening in the SCL. So it is our pleasure that we are having our Mr. Jatana to learn what is going on in SCL Chandigarh and what are the prospects of the students of our institutes, or like the students having microelectronics and VLSI technology, how they can get the opportunities and what are the scopes and challenges in this field in industry and academia. Now, before going to that, I want to introduce Mr. Jatana, that he is received his engineering education from BITS Pilani and worked at Rockwell Semiconductor, California, USA, where he was involved in design of R65 series of devices. He has vast experiences on CMOS design, device testing, characterization, test program development on ATE, silicon debugging, and process integration, porting over few technology nodes, starting from 5 micrometer to sub-micrometer nodes. He also worked as AMS Austria for 10 months on deputation for porting of SCL CMOS processes at their foundry. He has been instrumental in design of various ASICs and production vis-a-vis energy energy meter chip, single chip telephone, 12-bit ADC, 14-bit DSC, CMOS imaging, sensor CIS, signal processor SRAM, LVR, LDOs, and RAD hard devices, RAD hard devices, etc. His area of interest are low power CMOS device, analog design in DSM design, process enhancements, optimization in DSM error. He has also conducted a one-day tutorial in 17th VLSI design and test conference VDAT 15, 18 conferences at IIT Guwahati and VDAT 17 at IIT Roorkee, and has given several talks at various IITs and NITs. Has more than 15 publications in IEEE journals. So really we feel honored to have HS Jatana, Mr. Jatana with us. So please, if you uh, uh, enlightened us with your keynote for this FDP sessions for our new faculty members and students also.
Thank you, madam. And good afternoon to everybody. Is my voice and presentation is visible to you?
Yes.
So first of all, I would like to congratulate you and your university for having organized this particular design workshop. And it will be of immense use for the faculty as well as the students who are attending this workshop. And I express from the core of my heart gratitude to you for inviting me and giving me an opportunity to interact with the participants. So I believe this workshop is on analog design, but this being a keynote, I will not be focused on just one aspect. What I thought is proper, I will just tell you what are the trends and challenges in electronics and semiconductor. So I would like to talk over the next 45 to 50 minutes about the state of technology in electronics and semiconductors. You see, any electronic system is based on semiconductor elements. Whatever electronic system we make, there are semiconductor devices in that. So both the terms, if we talk about trends in semiconductor, is same as we are talking about the electronics. So I was fortunate enough to be a part of semiconductor industry for the last over 30 years. And what I will do is I will present a ringside view of this industry. Semiconductor industry has come a long way in India during the last 30 years, starting from few groups doing library standard cell library development work for their parent company, which was multinational corporation. Today, we see a very vibrant semiconductor ecosystem in the country, which is involved in end-to-end design of end-to-end chip, complete chip, not only the chip, but board level design, system level design. In fact, India can boast of doing around 40% of the world's IC design within our country. Though as a country, we may not have the IP for those design because we are working for all big corporations, which madam also told the names of few of them, Intel, TI, and things like that. So this semiconductor industry, CMOS started by 5 micron in the early 80s. Presently, 7 nanometer is in production at Intel, at Samsung, TSMC. They have planned for 5 nanometer, 3.5 nanometer, 1.5 nanometer FinFET. And after that, nobody knows. So now I will take a look, and the 3-4 main agenda on my talk will be the trends, mega trends, and how we are responding what are the forces which are driving this industry? What are the enablers of this semiconductor industry? And industry as well as the society, because any technology is for the benefit of the mankind. So it has to be in sync with the social values, with the society, with the environment. And I will talk about that. So first, mega trends. So let us go back. I will spend 2-3 minutes to as back as 1765. The first industrial revolution started in England in 1760 or 1765. What was that? That is known as Industry 1.0 or first industrial revolution. So there the primary means of manufacturing, they moved from manpower specific, manpower intensive to machine. So machines were, though they were crude machines, but machines were invented, and the primary means of manufacturing, they moved from manpower to the machine. So the fuel that time was steam as well as coal. So that is known as first industrial revolution. Started 1760 or something near about. Then industry 2.0, that is the second industrial revolution. It's also known as technological revolution. It started close to 1870, maybe a gap of 100 years from first industrial revolution to second industrial revolution, a gap of 100 years with the invent of electricity. So we have now superior electrical technology, which allowed even greater production, even ease to manpower, more production, more value addition. So this machinery, the equipment which were driven by coal and steam, they moved to electricity. That happened after a gap of 100 years, 1870 or 1880. Then again, after a gap of some 80 or 90 years, we have the third industrial revolution known as Industry 3.0, which is known as the digital revolution. The digital revolution. It started close to 1960 or something, somewhere around that, when the digital revolution began with the first computers. When computers, early computers, they were very crude, they were unyielding, they were increasingly large relative to the computing power. Relative to the computing power, their size was big, their power consumption was high. But anyway, those were those crude computers. But it was again a revolution. It transformed the lives. And now we are talking about Industry 4.0 or the fourth industrial revolution. It is the emergence of cognitive manufacturing. So I will explain more what do we mean by cognitive manufacturing. Industry 4.0, it is the automation. It is also known as the automation revolution. As the first revolution was known as industrial revolution, the second technological revolution, third digital revolution, and the fourth is the automation revolution. So the term was coined in Germany in 2011 by Bosch Industries. So this industry
Hello. Maybe due to network problem. Hello. Sir is disconnected.
Hello, but we are not. Mr. Jatana is not visible.
No, sir. Ma'am, I think due to network problem, sir is disconnected.
So, Prem, can you help, sir? Hello, Shobik. Hello, Shobik.
Yes, ma'am. Yes, ma'am. Yes, ma'am.
You see that what is the problem? Why he is
Actually,
not?
sir is disconnected due to some network problem, maybe.
Yeah,
So
I'm trying
we
to.
have
Yes, yes, yes,
we have
yes,
to wait
yes.
for some time. Okay.
I'm
Okay,
trying
okay.
to connect. Is it okay now?
Yes, yes, it is.
Yes, sir.
It
Yes,
is
sir.
okay. And please, all of you, unmute and image sharing. You please stop so that only for him it will be easier.
So yeah, I think it for the last 5 minutes it was. I will repeat some of this. I think I was talking about Industry 4.0, the fourth industrial revolution, which is also known as the automation revolution. So here, what this term Industry 4.0, it's a very recent term. It was coined in Germany by Bosch Industry in the year 2011. What we mean by is the machines not only they work themselves, but they are able to decide for themselves also. They are able to take their own decisions. So Industry 4.0 doesn't mean it's applicable only to factories only. It's applicable everywhere, like smart homes. What is the meaning of smart homes? Like we have lights, appliances, alarms, clocks. They are enhanced with digital capabilities. And what are those digital capabilities such as sensing, scanning, voice and facial recognition? So sensing, scanning, and recognition of voices, recognition of face, facial expressions. So that is the digital capability. So this is going to transform, and at the you see these are from application point of view. At the core of this is a chip, maybe a sensor, maybe a circuit, analog circuit, digital circuit, or memory circuit, but it's basically a semiconductor. So this is what about Industry 4.0, and people are also talking about Industry 5.0. This term was coined in year 2016. So this refers to people working along with robots. It's about robots helping humans work better for increased productivity. So there was a gap of around 100 years from first industrial revolution to second industrial revolution, a gap of 90 years from second industrial revolution to third, then the gap of around 70 from third to fourth, and from fourth to fifth, just a gap of 8 years. So this is how the technology is changing so fast. And the origins of four industrial revolution, there are plenty of, it's a merger, it's integration of various technologies as shown in this slide: virtual reality, your cloud computing, internet of things, and all cyber physical system, CPS, nanotechnology, genetic engineering, quantum, all these, they are the foundations of the fourth industrial revolution. So how we are responding to fourth industrial revolution? Basically, it's an integration of three words, three different words: physical, digital, and biological. So there are many devices which are there, which even in fact we are using also. For example, a handheld wrist watch which can take a biological function, say a heart, a blood pressure, a heartbeat. It can measure that. It's on physical body. It's a physical device, and control is by digital. So basically, digital means there's a chip. There is a chip which is sensing the biological functions and sensing online. So there is a merger of these things. So the way this virtual augmented reality is going to help the humankind in well-being of humankind, in tracing of various diseases, in making our lives better, it's amazing. So this is what various technologies now, they are integrated together. It is not that if you have to find a solution to a particular problem, one has to be conversant with everything. Now, you can say bioengineering. So there is nothing engineering and biology, they are not separate. It's a biotechnology. There is a mixing of these things. So we have to understand anatomy, physiology, along with physics, along with mathematics to be able to arrive at a solution of a particular problem. So semiconductor is everywhere. Silicon, some people call it as the steel of today. You won't find any field, maybe entertainment, healthcare, civil engineering, sports, where semiconductor chips are not used. Even you see a cricket match, there are small cameras put near the wickets, tracing the movement of the ball. So it is to that extent we cannot imagine a life without any chip. So this is what it is driving the industry. What are the factors which are driving the industry? Now, if I have a look at the last 50 years, 5 decades, let's start 1980s. 1980s started the information technology, IT. I'm denoting here as an IT. Lot of innovations in programming. Old programming were very, like we used to work on disk operating system, DOS, COBOL, Pascal. Then there was a concept of object-oriented programming. As the program sizes became bigger and bigger, so we defined as object and classes. It's a modular programming. If something change, you have to change just one module. You don't have to start afresh. There was a concept of windows. So all those things were a part of information technology. It makes the life of human being much easy. You can imagine a Windows, how easy it is for a layman without understanding even the core of computer, how it works, how assembler works. He can still handle the computer. That started in 1980s. Then 1990s came the biotechnology, which is denoted here as BT. Lot of new drugs, vaccines, innovative ways of finding new drugs and vaccines in biotechnology. Then 2000 came the nanotechnology, NT. So nanotechnology means placement of atoms in a particular fashion. So we are able to create 1D, 2D, 3D materials so that that material has a specific property. Maybe the mechanical strength is more or some electrical dielectric is more. So that is the nanotechnology, and India is in terms of publication, India stands third in the world only after US and China in nanotechnology. But where we are lacking, we have publications, but we are unable to convert those publications into ideas, into product, into dollars or money. We have very few products which are our own products, though we have huge number of publications. So the focus should be to convert those publications to product ideas. That is the nanotechnology. And then in the year 2000 started cognitive technology, where India AIML, artificial intelligence, deep learning, machine learning, and things like that. So publication wise, also there we are at position number 6 in the world. US and China are taking a lead there also. Japan is probably third, and some of the European countries. And 2020, in this decade, is started the quantum technology, QT, quantum transistors, quantum dot, quantum computing, and things like that. So Government of India, Department of Space and Technology has taken a lead by having an 800 or 1000 crore initiative for funding research in this area. So now when we talk of Industry 4.0, Industry 5.0, it's basically intermingling of these. It's integration of all these things. All these things, they are not like adjoint. There is a seamless integration. There is a mixing of these things. Now, what is igniting, what is fueling this semiconductor industry is the connected consumer. Consumer want to be connected every time, anytime, everywhere. This is what the requirement is. So consumer not only wanted a good mobile phone, but they wanted a to be able to send videos, not only videos, but a high resolution videos, a very high quality of display. And then further with AIML, consumer wants that software should be able to tell him, depending on tracing his choices, which product suits him. So things like that are improving. Then security is improving. Nowadays, voice recognition, facial recognition. So all these are based on AI/ML. So these applications, many PDA products are coming in the market with these applications. And similarly with the well-being, with the innovative method in the treatment, telemedicine and things like that, which are driving the semiconductor industry. So now many of these things, a good market, good potential, good segment of this market is the personal computing, mobile and gaming. If you see the number of chips which are being produced in the market, around 30 to 40%, they will go in that, in mobile gaming. You see the mobile phones, every 6 months or 1 year, these big mobile manufacturers like Apple, Samsung, they are coming up with a new mobile phone set with some additional features. Same with the gaming, same with the personal computing. And another big area which has now been opened up, lot of innovations, research, lot of data, how to decode that data, how to store that data, and artificially what to do with that data. So how to make machines which are able to take decisions, how to make machines which are able to learn these things. And then about the communication, finally the data has to be transferred from one place to another. So now you see, if we see the last 10 years, lot of growth has happened. Two examples are given here. Industry DRAM, like if you compare with the calendar year 2009 and 2019, it has grown. The density of the RAM has grown 12x time. Similarly, in any memory, static RAM, DRAM, it has grown 48x time. So, but now technology is moving, it's changing very fast. But this growth, it comes with the responsibility for sustainability. What it means is this planet Earth, also this growth should not hinder that. It should not create more pollutions. We have seen the negative effects, the side effects of the technology. People are talking about green technology now. So what we have seen is technology should not increase emissions. So that is the criteria. So there is lot of CO2, carbon monoxide emissions in the air, causing air to be polluted, affecting more diseases. So all these things have to be catered. How to control? Semiconductors can play a very important role in controlling all forms of pollution, air pollution, earth pollution, water pollution, because you are able to first out find out what is the level of pollution by sensors. Semiconductor devices are used everywhere. Then all these semiconductor devices, they need power. So from where the energy will come? Okay, so fossil fuels, coal, hydroelectric power is limited. Your coal power is limited to some extent. So people are working on alternate form of powers, maybe through wind tunnels, solar cells, and things like that. Then there is a water. Water is drinking water, fresh water is a scarcity. So how to effectively use that good water for human consumption, for agricultural consumption, which also needs a huge quantity of good water. And then there is a concern for waste disposal, huge amount of waste. Now electronic waste, number of electronic products are increasing. So there will be more and more of electronic waste, and it's not that easy to dispose of that electronic waste. So what are the technologies where we can efficiently handle those waste? Now, if we talk about today, the fuel for the semiconductor is the data. Data, I means the binary data, a string of 0, 1. So semiconductor, advancement of semiconductor industry is the foundation is to handle the data, is the power of data. Data is becoming very, very powerful. Whosoever has a data, he has everything. So data is the new oil. Data is the new gold, if you can say that. So the importance of data. So from where now, when we talk about data, so there is a lot of devices which are creating data. So data is created. What are those devices? Internet of Things, IoT, lot of devices, lot of sensors putting everywhere in homes, in vehicles, in factories, in machines. So they will create data. So once data is created by these sensors, these IoT devices, data has to be stored. So there is a lot of innovations in storage technology because the data is huge, and to store that effectively at low power, million and billions and trillions of bits is not that easy. So that also involve various improvements in memory technologies. Then finally, the data needs to be transferred from one point to another point, from a point where the data is created to the point where data is transferred and the data is processed. So we are talking about various data transmission like your Wi-Fi 6 and other wired and wireless technologies. That also we are talking how to transfer data, what are the very big, very huge bandwidths which are required for transmitting the data. And then finally, where the data will be processed, data processing centers, huge centers having very high computing power. Now the question is, a lot of data is being generated. There are some studies which say by year 2024, 2025, there will be 50 billion IoT devices or 1 trillion IoT devices. Each device, each person on an average shall have 10 to 15 IoT devices. Those devices, they are generating data online. Huge amount of data one device will generate. And that data is unstructured data. It's not a structured data. Each IoT device will generate the data in a different format. It's a unstructured data, meaning it's a stream of zeros and ones, unending stream of zeros and ones. It's an online real-time data. What we are doing programming is on structured data, structured program right now. So we don't know how to handle unstructured data coming from various sources. So that is how there are new concepts of programming, which is artificial intelligence is coming into picture, which is not a structured programming. What we are looking in certain patterns in that. We are looking in patterns in that data. I have billions of bits of data coming. So I will find a pattern. What is that pattern? Like face recognition. So if some criminal is there, I have his pattern, and in a huge amount of data, I will look for that pattern. So those algorithms, artificial AI algorithms are entirely different than the one which we are presently working. And these three things, Industry 4.0, autonomous driving and phone, they are going to be driving this edge computing. So what is the meaning of edge computing? I will explain. You see, I will give an example of autonomous vehicles. By autonomous vehicles, I don't mean only autonomous car. It can be autonomous pilotless planes, drones, trucks, and things like that. So in an autonomous vehicle, there are so many sensors which are put in the vehicle. Those sensors, they can sense the velocity, they can sense the acceleration. There are imaging cameras in the visible range, in the IR range, which can take images from all directions, all the four directions. And there will be some radar and sonar and things like that. Now, if a vehicle is moving at 100 kilometers on a highway, if some object comes from the front, so now the sensors will tell some object is coming, some image sensors will tell, some other sensors will tell. Now there has to be some processing unit which is able to decide what to do, whether to take a right turn or a left turn. If you have to take a right turn, by how much degree you are going at a speed of 100 kilometers per hour, or whether you have to stop. So the tremendous amount, amazing amount of data produced by each sensor, it has to be given to some decision maker, which is a processor, of course. So that is known as the edge computing. It is not possible to send the data to a cloud and to a data center where big computers can churn on the data and give you a decision. It's not possible because of latency, the time period. You need to decide within microsecond, within millisecond. So that is the concept of edge computing. So there will be computers sitting itself in the car, which are able to decide, monitor this data and take a decision. Same is the question, same is the Same is the scenario with Industry 4.0. Various machines, there are 20 different machines. A job is first carried on machine A, then it goes to machine B. If there is a defect in machine A, the machine itself sees that if the whatever assignment it was supposed to be done at machine A, if it is perfect, then that piece of object the machine will send to the other machine B for next processing. So the machine is able to take a decision on itself. And how that decision, that is because there are enormous number of sensors, IoT devices put in that factory, which are able to take thermal, visual scanning, and based on that scanning, they are able to find out if there is any defect or not, and deal with that defect. So the micro challenges now, the data is expanding every year. There are some studies you can find on the net, which they say the amount of data we have generated in the last 2 years is more than the data which was generated during the entire existence of humankind. So this is the amount of data which we have generated in the last 2 years. And that data every year is increasing exponentially. Another, the time to process that data and arrive at a critical decision is shrinking. We need fast decision based, it's an online real-time data. So we need fast decision. If it's long, there will be some consequences, maybe a missed business opportunity also. Another study says by year, after 3-4 years, by year 2025, 75% of the data will never be stored on a conventional data center. It's a edge data, it's a edge computing, like a moving vehicle. A moving vehicle online, huge amount of data, a drone, a huge amount of data is there. It's a edge computing, and after 1 hour, once the flight of that drone is over, that data has no value. It's only for history's sake. If there is some probing is needed, or you need that. Otherwise, it that data is not relevant. So 75% of the data will not see any conventional data center. It will be at the edge processing. So those kind of application are going to increase. So we have to store data, we have to process those data. You need semiconductor devices for doing all those things. So it's a basically a convergence in computational software. Some of the things software will do, some which software cannot do, you have to do by hardware, by a chip, by a package level, multiplicity of chip. Recently, you might be aware that Intel has announced this Riverview or Riverside processor. It's a single package. In the package, there are 4 chips. I mean, there are 4 different substrates. So these 4 chips are formed in 4 different technologies, one on 7 nanometer, another on 22 nanometer on a different substrate. So to upgrade the performance. So this is how the things are going to work. And at the core of this is the silicon. Right now, most of these devices in the semiconductor industry, 90%, the industry is $450 billion. They are based on silicon. They are based on silicon. And people are studying other materials, silicon carbide, gallium nitride, graphene, and things like that. So all those things, they will be driving. Like now 5G is one transmission technology, lot of efforts. There are many companies which are working to find solutions for 5G. So all those devices, modem and things like that, telecommunication chips for 5G. So they need very high speeds, more than 10 gigahertz, 20 gigahertz, which may not be possible on silicon. So one has to go for alternate device structures, alternate lithography, different sorts of materials. So this and a microsystem is again a small mechanical devices which we are able to make, like micro sensor or a microstructures, like a micro needle or a micro motor. So these micro means they are of the sizes of few microns, 50 micron, 100 micron. So they have lot of application in that, and the way they are made is same as a CMOS. The equipment is same, which is being used in fabrication of CMOS. So these micro actuator, microstructures, micro sensors, they are small components, MEMS components, which can which can identify, which can trace a mechanical uh, attribute like like velocity, acceleration, temperature, humidity. They can identify a gas, what sort of gas it is. So there are huge applications on these sites, this line, and you can see this slide. It gives a blizzard of IoT devices, which are basically a sensors for sight, for sound, for smell, for taste, for touch, for everything. We now have at least one sensor, which is a very small size, and you can as we know, there are small cameras which we can put inside the body. They can trace if there is any problem inside the body, so for body scanning. And so huge amount of applications based on these devices, which are made on silicon, which are semiconductor devices. Now I will skip some of these slides, and I will just go to the one. Now the concepts in computing is definitely going to change. Now earlier we were talking we were talking of processors and embedded memories, but now since the data is more, so we need a huge amount of memories, and we need to process data also. And we are talking about memory centric computing, which means we are talking about making memories with embedded processors. So processing in memory, the processing will occur where the data is generated. You store the data and do the processing there itself. So these kind of, and it has to be lower power and high performance. So these kind of applications which are driving the industry, and we are looking for all elements in a periodic table. Not only when CMOS started, there were only 15-20 elements which were used. Now we are targeting all elements in the periodic table. So we are targeting at the device level, at the how small device can be. As I told already, FinFET, it can go up to 1.5 nanometer. After that, some single electron transistor, some quantum dot or something other. And we are also talking about transistor channels, where you can put a germanium, or you can put a 3,5 compound semiconductor, or you can have some better material, so that you can improve the electron mobility in the channel. So the device structures can change, the device architectures can change. So there will be processors everywhere, but the architectures of each processor will be different. The type of processor which sits in the mobile, the type of processor which is required in a vehicle, in a car or a truck, can be different. So at present, there are 150 startups across the world which are which are working on development of various processor architectures, data processor architectures today, which have very high computing power and very low power consumption, because they are meant for edge computing, where they will work using a battery which is limited. So that kind of is the this is what the industry is going in that direction. So this is one slide which I got from Micron. As you are aware, is a memory making company. They do business more than 10 billion, 15 billion dollar. It's a big company. So they have, how they have done this industry 4.0, they have end-to-end automation of operation. Each machinery is connected with each other. It's fully automatic fabrication plant, fully automated fab. There is no human intervention in that. And full-scale IoT deployment for wafer imaging, hearing and feeling, thermal imaging also in that. So automatic data capture from each machine. And for defects also, there are programs which can see the defects, and the machine can take a decision what is the type of defect, whether it is critical or non-critical, what to do. So all fully automatic. And not only the process recipes, there is a joint data program where each machine, they are connected with OEM through this joint data science program for process optimization also. So much of devices, so much of AI ML being used in designing of these factories, it has resulted in 25% faster time to yield maturity, lower quality events 35%, increased output 10% increased output. So this is a type of factories where there will be less of human intervention. What engineers are doing, they're sitting outside the factory, evaluating the data, seeing the data, how the data is processed, and how to make more algorithms, better options for those. So this is the kind such kind of devices which are fueling the semiconductor industry. Everywhere you will find a chip. But now there are trends in energy and utilities also, because we don't have to spoil the environment. The environment pollution is increasing. So when we talk of smart cities, smart transport, city populations are increasing, diesel and petrol vehicles are no good. So you have to go for electric vehicles, mass transport also electric, and how to charge those things. So what is the integrated grid? So all those things are what are the alternative sources of energy. So those things also becomes a uh, important nowadays. And another important area where we have seen is even now the power transmission, where the power is generated, there are 20 to 25% transmission losses in India. And there has to be a balance between generation and distribution. That is why they do the load shedding. So concept of microgrids, e- energy efficient management of power. So semiconductor devices can help a lot in these things, in the power generation also, as well as the transmission, so that we are able to save on the 20% transmission losses. And some of the devices, wearable sensors, which those powermen can wear, so that for the safety also. So all those things are equally important, and same is the case of air quality monitoring and things like that, and IoT at satellite level also. So there, because satellite is an eye in the sky, so wherever you are, whether in the land or a mountain or a sea, at least the satellite can see you. So a lot of these functionality at the satellite level is also possible. And the small satellites at low earth orbits, low earth orbit means 300 kilometer to 400 kilometer from the earth surface, very low priced for a specific application. So those kind of satellites, not very big satellites which has a life of 10 years, because their cost is also more. But you need small satellites where the easy to launch, easy to make, and it is only cost effective for a particular goal. So those kind of applications are there, and their transponders, communication, all those are based on these silicon chips, these semiconductor devices. We will see a lot of devices in the wide band gap, high power applications. What those applications are, I will just show you. You have seen so much of these lightning devices, white LED, blue LED. So they are all based on compound semiconductors, all based on compound. There's no silicon in this. You can see these kind of blue lights and these kind of devices. So the power electronics is going to play important role in IT and consumer also, in automotive also, and in your industry also, rail transport, your electric vehicles, motor controls, wind turbines, UPS. So there is a requirement of power ranging from less than 500 watt to more than 1 megawatt. So you can imagine a device is small piece of substrate, maybe 100 square, handling 500 kilowatt of power. So it is possible, those kind of tiny transistors taking handling huge amount of power. So it will be used in DC AC converters, DC DC converters, UPSs, automotive, electric vehicles and things, motor controls and things like that. So those devices are made using gallium nitride. So this slide shows the property. What is the advantage of having a gallium nitride? Besides, it has more electron mobility, and overall figure of merit, if you see, the gallium nitride is 3000 and silicon is 1. So there are certain advantages by making transistors, high electron mobility transistors in gallium nitride. So I will just show you this one transistor, which is a on silicon on the right hand side. And on silicon, we can have 100 volt, 120 volt transistor. We cannot go beyond 120 volt. But using gallium nitride, we can have 2000 volt, 3000 volt, 5000 volt transistor. And only thing is, we will start with the silicon substrate. We will grow a nucleation layer, which can be aluminum nitride, and then a buffer layer, which can be a gallium nitride or an aluminum gallium nitride. And then we have to do band gap engineering to make a two-dimensional electron gas, which is known as 2DEG gas. So that is how this high electron mobility transistor works. This has huge amount of applications nowadays. So another area which is a GaN and gallium arsenide RF high frequency devices working more than 25 gigahertz. So those kind of speeds are not possible on silicon. So maybe this gallium 3 5 compound semiconductor devices, they play a role there. Now I will talk a little bit about Indian scene, Indian electronics and semiconductor ecosystem. The total worldwide market is $450 billion. We have good expertise in design as these global semiconductor companies, all global semiconductor companies are present in India, but we don't have a very good manufacturing base. And there are a lot of incubators and accelerators. They are set up at different universities, and like FabCI is being set up at IIT Hyderabad, CIATP. There are various entrepreneur parks. So this kind of infrastructure exists within India, and now India has lot of problems. There are many issues. So we have to see the problem as an opportunity, and we have to look for a solution. So the challenge is finding the right problem. So I will see list some of these areas. There are huge number of issues in India, but I have listed few which you can see here. I will just talk about only one, the clean drinking water. We have seen ATM, water ATMs at least I have seen at Chandigarh railway station. You put a 10 rupee coin, they will give 2 liters of clean water. So you can imagine a simple electronic circuit, electronic circuit and the equipment and how useful it is. People get ATM. It is not manned. It is automatic. So we have to find solutions like this. In energy conservation also, we are a power deficient and we lose power. Power is wasted. So how we can effectively, efficiently use power? The semiconductors can help in waste management, in security. You have seen in education, as you are doing right now. You can see how this semiconductor can play an important role in healthcare, urban mobility, and other areas of our this. So the business, I will conclude by saying the business leaders of tomorrow so will be those who solve real world problem in scalable, profitable, and sustainable way. This life has to go on. This human race has to go on. So technology should not have a negative effect. So just for one example, we are fighting with COVID. So there are a lot of reports which says COVID is a man-made problem. It's created by China. It's just like a bio weapon. So you can see how the technology can be dangerous also if used in a negative manner. So that is why what I meant by a sustainable, the use of technology by sustainable thing for the benefit of the mankind. So we have to see on those aspects, and there is a huge potential in India at the bottom of the pyramid. Because we have 135 crore population, we have to find solutions for the people who are at the bottom of the pyramid, and which includes 70% of the population. So there lot of devices are needed which can tell a farmer what is the humidity in the soil. Cheap devices which can tell the farmer how much water is needed. We are overusing the water. Clean water is already scarce, and we are overusing it. It may not be required. The sensors which can tell what is the micronutrients in the soil, whether he has to put urea, how much diammonium phosphate DAP the farmer has to put. Overuse is no good. So these kind of things, overuse of insecticide, pesticide is no good. So, but there is no way. Farmer doesn't know how much he has to put. So there can be sensors, electronics, semiconductors can help in those areas, and medical, plenty of such applications where the semiconductors are helping. So it's a overall. I will wind up with this by saying semiconductor is one field which will be there, which will be pervasive in all scales, in all fields of economy. And I think it's a very interesting field. And design of chips, design of your sensors. Nowadays we talk of smart sensors, sensor which reads a mechanical property, converts into electrical, needs a small op amp or a small amplifier circuit sitting close to the sensor. That is how it becomes a smart sensor. So lot of scope in this, and huge potential in India also. Or design already we are having a very good sound ecosystem, and maybe the manufacturing will also improve with the times to come. So it's an interesting field. Only thing is we have to focus at the right problem, identify the right thing, and work on that. So I think with this, I will wind up. If there are any questions, I will try to answer. So I will open this forum for questions.
Yes, I
Yes.
I have few
Uh,
questions and certain
yes.
things I'd like to share. So may I?
Yes, yes, sir. As Professor Professor Amitabh Sinha, he is our adjunct faculty UGC, Mr. Jatan, and he is like has a tremendous experience in digital VLSI design and embedded system design and processor architectures, and even in DSP field, especially. So I think he is the right person to guide us in future also. So please, Professor Sinha, if you can ask something from Mr. Jakan.
Yes. Hello. Am I audible?
Yes,
Yeah,
yes.
yeah, I'm able to find it.
Yeah. In fact, first my queries will be regarding processor architecture, and I would like to share my views as well. As what I understand, uh, today's technology is based on the open architecture, which maps a particular applications into architecture. That is in fact the state of the art technology, but I understand from different literature and also from different industries. Now, as far as the architecture of processor, memory, anything is concerned, it depends on three factors. It could be done either by architectural innovations, or it could be done by algorithmic innovations, or by device technology, innovation of device technology. But we have reached to a certain point where, in fact, not only processor, when we talk about the architecture of processor, we have to consider the architecture of memory also in view. Because if the memory is very fast, but processor can't support it, it doesn't have any meaning. Similarly, if the reverse is true, that is also the same problem. So when we think about the architectural innovations, we have to see the progress of the memory at the same time. Am I correct?
Yeah, actually, this is what I mentioned, because nowadays first of all, we have to see that the amount of data which needs to be processed is huge. It's not 100 or 1,000 times. It's a crores, billions, and billions of times more than which, and is expected to be more in the coming years also. Data is coming from many possible sources. It is unstructured data. It has to be processed, it has to be stored, and it has to be processed. So the amount of processing capability, the computing capability desired is huge, because we want instant decision. There are certain cases where we want decision to be taken in microsecond, millisecond, because it's a real-time online data. If the decision is late by
Yeah.
1 second, it has no meaning. So you have said architecture, you have to see what architecture suits for a particular application. Device types, people are working on making faster and faster devices. Right now we have 7 nanometer FinFET, which is used, maybe some improvement in other devices. And architecture, device, and the memory also. Memory innovation, you have seen Micron, if you go to the website, tremendous improvement in different
Yeah.
type of memories. And not only this, even another angle, which is the transmission, communication, because data may be generated at a sensor has to send that data wireless mode. That is why we are talking about 5G. Big bandwidth, huge amount of data has to be transferred from one point to another point. You can imagine in a case of a moving pilotless aircraft. So the lot of sensors, they have to transfer the data, not in a wired manner, but a wireless way, and data is huge. So those kind of people are talking about Wi-Fi 6, your fifth generation technologies in the communication. So all those things, you are correct. So that is the reason a general purpose processor architecture is not going to work. You see, I will give one example from the history. If we go back 15 years back, Intel, they are pioneer. In fact, all this scaling has happened in Intel. They are perfect in make designing processors. They design first 4004 4-bit, then 8080, 8085, 8286, 8386, Pentium, and things like that.
Yeah,
So they thought we are the leaders in microprocessor. Nobody can beat
yeah,
us. So,
but
but now when the mobile phone came, when the mobile phone came, earlier mobile phone were crude, but when more and more functionality was added, there was a need of microprocessor, and that time the Intel failed. Why it failed? Because their processor had 10,000 instruction sets. You don't need a processor having 10,000 instruction sets to be used in a mobile phone. So
yeah,
that time Qualcomm, it was a startup group, some 15 people, 20 engineers, they startup. They took a core from ARM and
yeah,
they modified that core to suit the requirement of the mobile processor. That is how
in this,
Snapdragon emerged. And
yeah,
now even Intel cannot beat the Snapdragon. So that is the because architecture, a universal architecture will not do. Specific
right.
architecture is the need. So
So
I
here I
agree, fully
would
agree
like
with
to
you.
add one thing. Here, yeah, here I would like to add one thing. Let's when we talk about application oriented architecture, and you correctly said about different mobile devices and all, let's take the example of cognitive radio. Now in cognitive radio there are two aspects, you know. One part is the functioning of communications, another part is the artificial intelligence. Now in recent times you must have noticed that Xilinx, they have announced a processor where in fact artificial intelligence engine is inbuilt within the processor architecture. But my view is, let's say take the examples, and a lot of automated tools are also there, you know, electronic design automation tools. And using these tools and using the concept of open architecture, your applications architecture, it will be mapped onto architecture, and at the same time, artificial intelligence processor will be there within the same chip. And that will help, in fact, one part will take care of massive computation for artificial intelligence task, and another will be the processor. And processor should not be like your typical von Neumann architecture, where a lot of sequentialism is there and parallelisms within the architecture is totally getting lost. So I think the innovative solutions for the architecture, at the same time, the technological innovation for the device technology, if they can be leveraged, that might give the perfect solutions to arrive at a processor architecture design solutions. That's what is my feeling.
I agree. There are different ways, different ways. That is
Yeah,
true.
there are different ways.
There is no issue, and many people are trying all different sort of things, and
Yeah,
it's good. And maybe all solutions may be good. And the point is here, there will be a lot of emphasis on these semiconductor devices,
yeah,
new and new architectures. A lot of applications are going to emerge, and there is a race between different companies. As you have seen now, 5G. So you have to make chipset for 5G. One or two companies have already come out with their chipset. So whosoever comes in the first, making an efficient low power chip, he takes over the market. So it is like that only. So here and this the driving force for this semiconductor has to be centered around data, because finally you are processing a digital data. So this is what, because all these sensor devices, all and memory and processor, they will become the heart of any industry.
yeah,
Without this, you cannot imagine a situation. Even a small thing, a home security system, you can see a lot of data. It has to be stored. It has to be processed automatically. You have facial recognition and all those things you can put in AIML also. So it's a merger of all these things: good software, good devices, good architecture, good communication. So it's basically a merger. A solution has to be a merger of all these technologies. And a human angle is also there. Cognitive technologies, AI, ML, deep learning, that is definitely, it's going to have a huge business in the next 5-10 years. Each product, everywhere it will be used, including defense. Now defense are also saying how they can use effectively monitor the border using AI, ML. So that is agree that I agree with you fully on this. It's an interesting field. We are also learning some of these things every 6 months. New things come up, and we are also a student, and nobody can claim to be an expert in this field at least. So all are students, all are working, and all are learning new things from each other.
Thank you. Uh, Thank you once again, Mr. Chatan, for your illuminating or encouraging talk for the students and faculty members as well as the researchers, that what should be the new direction of research and technology, what is the trend of the technology we are going for. And can I ask one just to interaction that have some questions regarding the device also, and some points that you were telling about the data processing, and you have shown one chip or the where a memory device where there are different technology like 180 nanometer is there, maybe 35 nanometer, maybe 22, maybe 14 and 7 nanometer. Is the thing is that because of this processing speed and maybe the interfacing circuitry where the processing and the addressing and the data fetching and everything, there may be a sequential or the problem of different clocking speed and delay and others, maybe responsibility may be another thing. So in that case, because of this kind of integration of different technology, or it is the for other purposes?
You see, you have rightly said, the memory, each application, it depends on two things. One is what is the access time and how much data you have to store, how fast should be your memory, and how much should be the density, like how much data you have to store and how fast it should be the memory. Third angle which is coming is the power. You see, in one way, if you want to design a chip which which works very fast, then it takes more power also. You see, as from physics, if you see, if you want a vehicle which moves at a high speed, it consumes more fuel. So same is with the chips. If you want to make a device which is working very fast, it will eat up more power. Like your power is FCV square. So that way, but nowadays, what we need is we need a fast memories, huge memories which can store, huge means which can store more number of data, and it has to be low powered because of edge computing. Wherever edge computing is not there, like data centers, there you can they are wired with the 220 volt on power supply. Those applications are different, but there are huge plenty of applications which are on the edge, so there is no wired power. So it's they are dependent on battery. So you need low powered memories also. So that is how a lot of work is being done by different companies, and Micron is leading there for designing of such memories which have very fast, less than 1 nanosecond SS time. They are so fast memories. And now there the design architecture will help, because you cannot make a huge memory having access time of 1 nanosecond. There will be some cache. That is why the definition of cache, first cache, second cache, you want so many bytes very fast, and so many bytes not that fast, you have to split. So the concepts of low power design, voltage scaling, your functional scaling, so all those things come into picture that way. So, and people are talking of different materials, different device architectures, different processes. So, and overall system design concepts in the overall system design also to arrive at a particular application. So, it is you have to target all angles to have a good, efficient solution. One thing is not targeting only one aspect is not sufficient. Device
Exactly.
is also getting saturated. You cannot improve the device further. Your architecture is also getting saturated. You cannot improve it further. So you have to see many aspects nowadays to find. That is how the Intel came out with the one processor which has 4 different substrates. Package is one. So the packaging also playing important role. 3D packaging. From the outside, you will find it's a one chip, but inside 3 or 4 many chips are integrated in 3D, so that there is no parasitics at all. So people are thinking out of box solutions, and there is a applications are huge, and solutions also will come. Definitely, it will come. Any
Okay.
other question, please?
Thank you. Thank you so much for your
Thank you, madam. Thank you,
uh,
madam.
different
Yes,
in
sir.
detail.
Sir, at, Thank you for your nice presentation. Sir, there is a question from the participant.
Yes.
He wants to know, is there any internship program or opportunities?
Internship. Yes. Is there any internship
Internship
program?
was there. Students
Internship.
BTech, MTech, PhD, they were coming for internship at SCL, but now because of COVID, it is suspended till December. And from we will take a decision by December. If things improve, then maybe by January students can have a internship. Another thing is IIT Guwahati, they are running a student internship, and I am associated with them. And there they, I think, online, the students are sitting at home online, and we are giving some design modules to them on using those free tools, because the standard tools students cannot have at their homes. So by till next 2 or 3 months, where mobility is a concern, so this online webinar and this only is possible. It has limited use, but there is no other option. And finally, once the this travel thing improves, the disease is contained. I think it is, if some student want to come here SCL, it will be very useful. They can learn how the actual design is done and the product is made. Not only the design is one part. So finally, you have to make a product. So many things goes into making that product, and which the designer has to take care while designing also. So one has to see
Yes.
physically, have a feel of it, have a look at it. So which is not possible by sitting at a home or watching a video. It gives limited thing. But presently, for the next 2 3 months, I think we have to live with this only. And the internship is there. Yes, we give, and the students, they get benefited as per their feedback. They learn a lot, and based on that, they get a lot of awareness and good job opportunity also. It's useful for them. This is what the
Yes.
students have given the feedback.
Thank you. It is a for the participation on internship, they have to fill up the form only, or have to write up some proposals also.
Yeah, no, they have to fill. They have to go to our website and send their biodata. That's all. Website
Okay.
is there. Link is there. Student internship
Okay.
or student training. Some link is there.
So we have the great scope, as we have the microelectronics and VLSI technology, VLSI design, both are in our syllabus curriculum. And we have the system design, we have the group project, and even in individual project also. So really there is a scope to collaborate or the take internship from our institute, so that really our student can do or learn something. That is our intention from our
Sure,
university.
sure,
And
madam. So
one
your
and
university is based where, in which city? Is this Kolkata or it's somewhere else?
it is the main campus is Calcutta. It was earlier in Calcutta, Salt Lake, but now as we are expanding in not only volume, the number of courses, number of entries, everything is going on increasing. So one of the campus is shifted to Horingata, that is near Nadia district, near Krishnanagar. So
Oh,
we are there. The residential campus is there. So we are having increasing our microelectronics laboratory also there for some scope, so that we can fabricate some synthesis method, or kind of very very small, but it can be like the total. They have the awareness of regarding how to fabricate and complete the thing. That is a great our desire to have the awareness in among the students. So if they are going there, they also be able to, and faculty can join there with them to take the flavor of kind of laboratory visit, or kind of training they can take from your SCL. Faculty members can do that, can join there. Hello, hello, hello.
Yes, ma'am. Yes, ma'am.
But maybe Mr. Jatana is not connected, I think.
Hello, Jatana sir. Are you able to hear this?
yeah, sure. When the things improve, yeah, sure. No,
Yes, And another very good aspect is SCL, as we are very much associated with the like fabrication, design, core hardware part. But nowadays you are showing some of the capabilities of IT people also, because there are information, huge data is coming. And one more question about this, that you are telling the processor is taking care, the memory is taking care of the processing. That is kind of pre-processing case, or it is the throughout the processing and the up to the decision making that you are talking about, the processor in memory that you were telling. Hello. Hello.
Ma'am, Jatana sir, I think has disconnected right now.
Okay, okay.
And if he
Thank you.
joins, we'll let you know.
Okay, next session, if he will be joining, then we'll be asking him. And really, we are motivated and we are illuminated by his nice talk and what are the future opportunities for the students as well as for the faculties in this direction, that we can come to know. That yes, there is a huge scope of having or passing out of these degrees, and there is VLSI design also has a very good scope in near future. So by thanking once again to Mr. Jatana, I can now, Mihir, can you now take the responsibility to take the next session, to start the next session
Please,
from Damodara, I
ma'am,
think. Yes.
Please introduce ma'am, because
Yes.
yeah,
Yes.
the next session will be presented by
Yes, ma'am.
Mr.
Damodar
Damodar.
sir has.
Yes.
Ma'am, I request you to introduce Mr. Damodar.
Yes, you can do also.
Sir, are you able to hear us? Hello.
You
Damodar
can
sir,
do
please
also,
unmute
no
your
problem.
mic.
I'm there, Mr. Mihir.
Yes, sir. Yes, sir. Yes, sir. Ma'am, please.
Yes, we are happy to have the Interpol Technologies with us, and Mr. Damodar, MS Damodar, is business head of Interpol Technologies, which is the sole vendor of this yes, sole university program conductor, and they are the actually they are conducting the university sessions, university collaboration for innovating things and for collaborating the design part also. And they are the sole distributor or the sole agent of the Cadence in India university program. So Damodar is a business head at Interpol Technologies and he's based out of Bangalore, India. He is primarily responsible for application engineering and consultation for customer across India for defense, aerospace and corporate sector. Prior to joining in Interpol Technologies, he was the IEEE as product manager, the contributing industry liaison to semiconductor industry, and he was actively involved in IEEE standard association activities, System Verilog, and UPF work groups. He also supported from IEEE president for his contribution for proliferation of standards and learning activities. Damodar carries 17 years of industry experience with core expertise in front-end design and verification, board system design, and with experience in telecom equipment, medical system, aerospace automation, and automotive hardware system design. Throughout his career, he supported educational and competency building activities. He contributed in developing learning solution in the space of RTL design, verification, timing analysis, system design, and more as a subject matter expert. Received appreciation award for his contribution in competency building initiatives for internal engineering resources at Wipro Technology. Currently, he is supporting IEEE in education activities. He is actively assisting Electronic Sector Skill Council of India in developing national skill qualification framework for engineering job profiles in VLSI domain that include design and verification engineer, system design engineer, and more. Damodara holds MTech in VLSI and embedded system specialization from Vishishtara Technology University, Karnataka, and BE in electronics and communication stream from Bangalore University. So with this introduction, I welcome Mr. Damodaran to take the session and start his expertise so that the student and the participant can be illuminated and motivated. Thank you. Thank you,
Thank
Dr.
you.
Damodar. Yes, yes.
Thank you, madam. So let me. Mr. Mihir, is my screen share is working?
Yes, it is working.
Yes, sir. Yes, sir.
Thank you.
Yes. Please make it large. Slideshow view.
Yeah, sure. Good afternoon, all. So welcome you to this webinar session on analog IC design. What is the contemporary needs and the opportunities, and I'm also going to throw light on Cadence University program. At my end. So before getting started with the proceedings, I would recommend all of the participants to follow these guidelines. So keep yourself on mute and don't turn it on during the course of the webinar. If you have any questions, please share those questions on the chat box. I'll be happy to address them during the QA session at the fag end of this session. And the webinar is going to be focused with the features and the capabilities of the Cadence EDA tools also for your information. And if in case if you have questions on any other EDA tool flows also, you're open to share. And all queries are related to tool setup, license access, design fixes, right? If in case if you are already working on full custom IC design flow, analog circuit and layout, so you are feel free to contact our technical support team, cadence_support@ntuple.com. So we have a support team, sitting across India. They'll answer your queries. So to begin with, before getting into the concepts of the design flow, at NTUPL, we are a design services and IP and product development company, having our presence in VLSI, electronic system design, RF and microwave, and electrical drives for renewable energy systems, even with extension to electrical vehicle, and also on emerging technologies like IoT and data sciences, where we work with our partners, on hardware solutions coming in from our end, and as well as the software and the firmware components coming from our partners. And we also work on mechanical engineering streams like computational fluid dynamics and FEM and CAD and CAE modeling. And in these technology domains, we cater to the multinational clients of ours in India and as well as overseas. And we also cater to the defense and aerospace customers of ours in India and as well as overseas. And we also share our learnings and our experiences with the academia network pan India through our activity known as EASY, NTUPL Academia Solutions Initiative, through which we share that experiences with the academia network. So this is briefly about NTUPL as an organization. So with that background, let us get into the core part of today's session. Okay, so Mihir, how much time I have for the session of mine?
Yeah, you have up to two you have. Yeah.
Okay, so 40 minutes. What I
Yes,
have.
you can take 15 minutes more, as you have already, we are going late some, so you can take up to 250. Okay.
2:15. Okay, sure, ma'am. Thank you. So then I'll try to make the things as crisp as possible. Okay, right. So we'll get started with the very quick thing. Uh, Generally, there is a perception in the VLSI world, okay, that what we see at the academia and what we see in the industry, okay, the perspectives are different. Yes, the answer is definitely yes. The perspective in which we look at the VLSI segment in the industry and in the academia, it is different, because VLSI in the industrial domain, it includes both chip design and as well as hardware design, which the industry calls it as board system design. So, which in academia framework, we call it as embedded hardware design. So now coming into chip design, we have two broader segments, ASIC, and under ASIC you have full custom and semi-custom. So I'm assuming that all of you are quite aware about the ASIC design flow methodologies. So in ASIC, okay, you have full custom and semi-custom, two different methodologies which run parallelly. The moment we say application specific integrated circuits, we can take examples of a microprocessor, memory, microcontroller, and as well as a digital signal processor or an FPGA. So all of these are examples for application specific integrated circuits. Now, if we take a application specific integrated circuit, then by and large, since I'm assuming that all of you are aware about full custom and semi-custom, then it is important for us to understand which pieces of a application specific integrated circuit follows full custom methodology and which pieces of the ASIC follows semi-custom design methodology. So in order to understand that, let us take a quick example. For example, if we take a chipset, in the chipset, you have your process logic, right? And this process logic, okay, right, has arithmetic logic unit, okay, right, and master bus interface and internal memories. And apart from that, you also have on-chip memory, power supply block, and you also have IO interfaces controls, okay, like SPI, I2C, and Ethernet, right, USB, and so many other interfaces, okay, which your processor core, okay, basically drives. And apart from that, you also have lot of GPIO interfaces, which your core logic would be driving. Now let us take a look at the memory and your power supply. For example, your power supply, it has to drive power to all the elements which are present within your chipset, one thing. And at the same time, it also should provide constant voltage and constant current, irrespective of the variation of the power supply and the temperature and the ambient conditions. And at the same time, you also have a memory, right, which basically interacts with your core logic computation and also does a lot of exchange of information with the external world. But here, if we look at the internal architecture of these blocks, for example, if we take a memory, then if we go to the lowest level of abstraction of a memory, right, those memory elements are made up of memory cells. Those memory cells may be an SRAM memory cell or DRAM memory cell or a specific category of memory cells, which might have been built from the full custom IC design approach. That means to say that characterization of those transistors, right, and devising them, okay, right, as per your requirements, and then you, right, populate them according to your circuit topology, right, and you build a memory cell where you can store your binary data. That is how you bring up the memory architecture, okay, from a basic cell. So if you are following such type of an approach where you build a basic cell with according to your requirements, that means power and the latency and area of cross section and everything you decide according to your own requirements, okay, right? And if you build a cell and then you keep on, right, increasing the number of cells, okay, right, or else you package the number of cells and you build a right hierarchy, okay, to implement a complex structure, right? So such type of an approach, what you call it as full custom IC design. So same thing holds good for your power supply also, which will have, right, lot of computational elements, which basically takes the external analog signal, okay, which comes from it, and it basically, right, does a lot of computation, a lot of processing of the signals which are coming from the external world. It may be a DC DC conversion or else AC DC conversion, all of that depending upon your requirement, and then it sends those signals to the other processing elements which are present within your chipset. So your power supply is another element which is built using full custom IC design approach. Now let us look at semi-custom IC design approach. For example, if you take a look at your core digital processing logic, the core digital processing logic has registers and as well as arithmetic logic unit and lot of right decision making tree branches, okay, right, as a core logic, right? All of those elements, they are not built using once again your standard cells. What do you mean by that? For example, when you build a arithmetic logic unit, you essentially won't start with, right, building your standard cells all the time. Okay, please be noted that I am giving some uh, 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 basic clarifications also here. So as a result, if you are having any questions, please share your questions on the chat box. Every time when you are building an arithmetic logic unit, or every time when you are building right, a complex decision making tree, right, in the digital core logic, you don't build that entire framework or else entire design by building standard logic cells, okay, from the scratch. That means you don't start building your inverter, right, and NAND, NOR, MUX, right, and D flip-flops, and then you start implementing all of that. If you recall, probably none of us, we might have done that every time. Yes, we do work on the standard cells like inverter, NAND, NOR, XOR, XNOR, and as well as multiplexer, D flip-flops, all of these elements we will build still following the full custom IC design approach. But the moment we have to build a complex logic, then what we do is we either follow a modeling approach or else we follow a HDL approach. That means you write a Verilog code or VHDL code, or else you create a model representation, okay, using any high-end programming language, and then you basically simulate to verify the functionality of the design, and then you basically synthesize and you map your entire functionality with the help of the standard cells. Now the question is that these standard cells are not built by you. Somebody gave those standard cells and you are utilizing it. That means you cannot customize your design beyond a certain level. That is the reason why it is known as semi-custom IC design flow. So simple crude examples, right, example which I can share with you to make things very simple is that if we are constructing a home, then if we are setting up a brick clan, right, and building the bricks on our own so that it can have the proper, okay, right, baking mechanism so that it can hold the required amount of moisture, okay, required amount of density and the weight, okay, size and everything, and even mortar we are making on our own and we are constructing our home. Then if you are following such type of an approach, then it is known as fully customizable. Whereas in case of semi-custom, we are building a home, but we are ordering the bricks from X vendor, okay, right, mortar from Y vendor, steel and other raw materials which are needed from another vendor. So what we do, we integrate those solutions and we build all the blocks which are needed to construct our home in a very quick fashion of time. That is what you call it as semi-custom IC design. So if you are following a similar kind of an approach as far as your integrated circuit design is concerned, then it is known as semi-custom IC design. So By and large, what is the takeaway for us from this slide is that if you take any application specific integrated circuit, you do find lot of elements like standard cells, right, and as well as power supply, right, data converters, right, and memories, which follow, right, which are built using full custom IC design approach. Whereas you also find lot of other blocks like your memory controller, right, logic, and as well as your processor core logic and internal registers, lot of other elements which are primarily built using semi-custom IC design approach. So both the methodologies are widespreadly used in the industry. So whether it is design services company, product company, or else a foundry, right, any company for that matter, all of them, they work on both full custom and semi-custom IC design flow. Continuing further, let us take a quick look at, okay, right, how the detailed design flow goes, okay, right. When it comes to semi-custom IC design flow, you have four sub pillars, okay, which manages the entire flow, okay, or else it is subdivided into four sections. First step is your RTL design. Second step is RTL verification. Third one is synthesis, and the fourth one is physical design. So now, from the industry standpoint of view, okay, how this entire sections, okay, they spread across. For your information, RTL design and verification offers nearly 40% of the job opportunities for you, whereas physical design offers, right, 30 to 35% of the job opportunities, and all the other streams put together, okay, offers, right, another 20% of the job opportunities for you. Okay, so now coming into RTL design, please be noted that once we have a requirement information which is clearly known to us. What do you mean by that? For example, if a product company or else a design services company, right, starts with a semi-custom IC design flow for their chipset, how do they start their work? Okay, it all starts from a process known as market research analysis, right, where they try to analyze what is the existing, what is the limitations or improvisations needed from the existing product or solution or existing product or chipset. Then they try to capture what kind of an improvement or enhancement that needs to be added. That is what you call it as market research document. And once the market research document gets created from the market analysis team, then the architecting team try to build a framework of the design which can fulfill that requirements, okay, which is being projected by the market research document. Architecture is basically like a blueprint of your entire construction of a home. Similarly, architecture of an integrated circuit is a blueprint which basically going to have information such as the detailed block diagram representation of the entire design, and with internal blocks also, okay, represented at a very top level, and how the signals are flowing across the entire design, and how much amount of power the entire design consumes, what is the area of cross section which this design might fall in need of if you roll out a chipset, and what is the right performance specifications on which you want to sign off the design. So those are the kind of, and plus even the timing diagrams information, right, and all that information basically gets captured in your architecture. So that information gets captured in the industry in a document known as a high level design document. And once the high level design document gets created by the architecting team or else the architect guy, okay, who builds that top level design document, which is known as high level design document, then from that you will start defining each and every sub block. What is the internals of each and every sub block? What are the signals which are running into each sub block, and how those sub blocks are communicating with each other? So the document which captures that information or else the phase of the design which you do that job, what you call it as micro architecture, where the internals of each and every block is captured, and that information, okay, will be given to the design engineers in the form of a document, and that document, what we call it as low level design document. And generally the design document acts as a primary input both for the RTL design engineers and as well as for the verification engineers. Okay, so RTL design engineers, they use that document and represent that design using Verilog HDL or VHDL or system Verilog, depending upon the policy and the guidelines of each and every organization. And remember, there are other design entry approaches also which are followed in the industry, like block diagram, flow chart, okay, right, state diagram and state machines. For example, if you take aerospace industry, right, even today they follow block diagram based design entry approaches, because the entire architecture framework is going to be so complex and the design requirements are so complex, it is very challenging to represent such type of designs using RTL. Okay, so hence they follow block diagram based design entry approach even today. So once if you represent your design using Verilog HDL or VHDL, right, or system Verilog, okay, right, using using one of these languages, then that design has to be verified. So the verification of that design basically is the second step, which we call it as RTL verification. So here, the reason why we call it as RTL design and RTL verification, it is registered transfer level representation. Remember, there are various levels in which you can represent your design. Here, we are representing the design in the form of interconnected logic blocks. That's the reason it is known as RTL. So here, once if you represent your design using RTL, that is Verilog or VHDL, then you need to verify. So if you want to verify your design, you need to build a test bench. So once if you build the test bench, remember, if you are already familiar with the concepts of verification, it is well and good. If you are not familiar with verification, please be noted that verification is a procedure very similar to the way you might have tested your basic hardware using a trainer board in your lab, where you insert your integrated circuit and you feed all your logic inputs, and whatever outputs you want to monitor, you feed it into some display LEDs. Same thing in a RTL verification also, the signals which has to be driven into your logic, okay, that is digital representation of your design, will be driven by you, and at the same time whatever response that block generates, that also will be analyzed by you with the help of, right, tapping those signals. So the environment which basically gives the feed of the signals and also captures the response which is coming out of your design blocks, what you call it as verification environment. That verification environment will have blocks such as a driver, right, which basically feeds the stimulus into your DUT, design under test. And once if your DUT produces the response, then it captures that response and it, right, verifies that with a golden reference output which is expected out of your design. So the block which basically manages your expected output with the actual response, what you call it as, right, response checker, right? And once the response checker gives you the results that everything is matching 1-to-1, then you say that my design has met the verification goals. So if your design meets the verification goals, then you enter into your synthesis. And verification has a lot of procedural things internally to it, because today, as you notice, if you take any SoC or NOC chipsets, their design specifications are so complex, right? Because so many powerful capabilities which we are keep adding into those chipsets. So what is happening is that the number of design corners which you need to manage as far as your SoC or NOC is way too huge. So as a result, right, when you are managing your verification, you need to ensure that each and every corner of your design is thoroughly verified. Simple example is, for example, if you take a 4-bit binary up-down counter, right? If we elaborate the specification of the design, it goes like 4-bit binary up counting, down counting, then synchronous clear and asynchronous reset. That means up counting, I have 16 counting sequences, down counting, I have 16 counting sequences, then I have synchronous clear and asynchronous reset. So that means I have 34 conditions to check to ensure that whether my counter is working properly in every which way. So imagine if those many number of corners what I need to verify for a simple counter, then imagine a chipset, imagine a processor, right? The number of corners which your design is going to face is in millions. So the question is that, can you verify each one of them one by one manually? The answer is no. That is where exactly you have, right, lot of automation, randomization, right, and as well as assertions and lot of other things, which is simplifying the verification for us with the with the advent of system verilog and as well as UVM, and then with respect to, right, advanced verification methodologies such as even SOC verification also. So once if your design thoroughly gets verified with the verification flow, then you take that design which is functionally verified. Remember, at this point we are only verifying the design functionally only. That means the functionality of the design we are verifying. We have not yet verified how much amount of area cross section that design occupies, and what is the number of what is the power occupied by the design, and the performance of the design. That means the speed at which the design can run. Those things has not yet been tested. So in order to test that, your design has to be translated into a logic circuit. The process in which your Verilog RTL or VHDL RTL is translated into interconnection of logic gates, what you call it as synthesis. So here we call it as logic synthesis because you are translating your RTL into a gate level logic gate level representation. So that's why it is known as logic synthesis. So logic synthesis generates a gate level netlist for you, which is also known as GLN. So once if you get the gate level netlist, there is no guarantee that under all the empirical conditions, the expected input drives that logic, and it also produces the expected response. So in order to take care of that, you need to do the pre-layout DFT checks for your design. That is what you call it as designing for testability, to ensure that you create a boundary logic around your core such that no spurious signals enter into your design, and also it won't produce unexpected responses for you. So the process in which you actually do that job, what you call it as DFT, and then once if you are done with your logic synthesis and DFT, you go for logic equivalence checking. Remember, synthesis, it is basically a procedure which not only generates a gate level netlist for you, it also brings in lot of optimization for your design. So as a result, once the electronic design automation tools brings in optimization, you need to ensure that your design is still functionally correct as the way it was earlier. So in order to do that, you compare the gate level netlist with its own Verilog file from where it is being generated. The process where you compare the gate level netlist with its own RTL, what you call it as logic equivalence checking. So after logic equivalence checking, where you have done the functional analysis to the next granularity level, you tend to perform the timing checks of your design, and you are doing it before you are converting your schematic, you are converting your gate level netlist into a layout. That's the reason it is known as pre-layout static timing analysis. And remember, in timing analysis, you have two different approaches: dynamic timing analysis and static timing analysis. But static timing analysis is the one which is very commonly used in ASIC design flow. Okay, right? So why and all, okay, right, is not the scope of today's discussion. If you have any questions, you can raise that during the QA sessions. So once if your design meets the timing, then, right, you basically generate a gate level netlist, right, which is timing wise checked also, or else meeting the timing qualification also. Then you take the design and you basically translate that into your mask layers. Okay, right? So where the gate level netlist, which is in the form of interconnected logic gates, is translated into, right, a layout. And that such type of a layout, now it goes through a physical design which includes APR, automatic place and routing. Then once again you verify the functionality through logic equivalence checking, and then you do the parasitic extraction, right? And after that you do the post layout STA, that is you do the timing checks again, and if your design meets the timing, right, then you proceed further towards physical verification. If your design fails, okay, then you do the APR again and you rerun through the entire stages. Then in physical verification, you basically do the DRC, design rule check, ERC, electrical rule check, okay, right, and as well as even layout versus schematic checks. All those checks are done in physical verification. And once if you are done with that, you get into DFM, design for manufacturability, where antenna and OPC checks are done. And once if those checks are successful and no bugs are being found, okay, then you sign off your design into the tape out. Now, physical design is a very complex process by itself. So what is that process involves? It involves process like partitioning your logic. Okay, what do you mean by this? For example, if you have a design, what you are seeing here, then the design is nothing but interconnection of logic gates. Then those logic gates has to be fragmented with a partitioning logic, right? And that partitioning of the complex design also follows certain guidelines of the design, so that you can effectively partition your design, and at the same time you can plan for placing those blocks at distinct locations in your die area. It is very similar to the way the planning of the layout map of our entire home is done. For example, in which corner the common area should be decided or else should be planned, and in which area we should have the kitchen and other utility areas and everything. Similarly, when you are partitioning your entire complex logic, you should decide that where the core processing logic should be placed, and where the power supply block should be placed, and where the memory cells, memory blocks has to be placed, and memory controllers, IO blocks, IO controllers, sensors. So you need to define the partitioning of each one of that block. That is what you call it as partitioning. So once if you do the partitioning of those cells, different elements, which is part of your SOC or NOC, then you need to define the planning floor planning map, okay, for each one of those cells. That is what you call it as floor planning. And once if you have done the floor planning and identified what should be the positioning of each one of those blocks in your design, then you start placing them one by one. And here comes automatic placement and routing, because the electronic design automation tools, they have been automated in such a way that they can take a decision on where to place these blocks. Remember, generally the electronic design automation tools, they are very good when it comes to clock signal routing, okay, but when it comes to data signals routing, right, they are not really that efficient, okay. And that is where exactly you have to play a lot of role, okay, in order to optimize your design. So in order to do that, okay, right, you follow the step known as APR, automatic placement and routing. So once if you place your cells in the confined area in the process of floor planning, then you basically do the clock tree synthesis to ensure that the clock signals are very well distributed across the die area in your chipset. That process, what you call it as clock tree synthesis, right? And once if your clock tree synthesis gives you the proper timing response, then you once again go for the timing closures. And once if you are done with your timing closures and power analysis sign-offs, then you go for your physical verification and sign-off, and which subsequently leads to fabrication and then packaging and testing of the chipset. So here, this is the very, very detailed flow of semi-custom IC design flow. So now, in case of the semi-custom IC design flow, what you saw, which has such a detailed flow, the physical design and verification stages, it is also known as physical backend, because you have your design being translated into a layout and you are managing all the steps which are subsequently you are doing it, right? So that is the reason it is generally in common interactions, we also call it as backend design, which includes floor planning, then placement, automatic placement and routing, clock tree synthesis, and timing sign-offs and power sign-offs. So those are the stages which are involved in it. And you can notice that the accuracy and the time margins which is involved, okay, right, in these processes, as you can notice here, as we go further and further into the design flow, the time margin also reduces, and even the number of errors we'll try to minimize to the minimalistic extent. Okay, so that is how the entire design flow generally goes. Now coming into full custom IC design flow, remember, in full custom IC design flow, you have once again the design requirements which are captured in the form of an architecture. And once again, when you want to represent your design, then the design can be represented using schematic based design entry. Then you may ask a question that in full custom, in semi-custom IC design, we had HDLs, okay, to represent our design. Can't we have such type of a flexibility here in full custom IC design? Yes, of course you have. You have languages such as Verilog AMS, right, and E and Vera and other programming languages which are basically used to represent your analog basic building blocks also, okay, or else your designs can also be represented, okay, with the help of those programming languages. So what are the limitations of those programming languages, why they are not very right commonly used? I'll address that in the next slide. But please be noted that more than 90% of the industry, they prefer schematic based design entry for the full custom IC design flow, because managing the design is far more easier in schematic based design entry. So then once if you are done with your schematic design entry, you need to perform your schematic simulations to ensure that your schematic is producing the expected response as per your microarchitecture and architecture. So once if your design meets the specifications, then you go to the layout part of your design, and once again you perform your layout simulations, and you get into physical verification and parasitic extraction. And once if you are done with your parasitic extraction, you go to the post layout spice simulation, and if your design meets the specifications, you get into the fabrication. Now the question is that, right, why we have to do the DRC and LVS even in these stages? Remember, the layout rules, okay, right, has to be in line with your, okay, foundry guidelines, okay, because eventually you may be getting it fabricated by your own in-house foundry, or else you may be outsourcing it to a foundry. So you need to ensure that your layout follows the given technology rules, design rules, and as well as the layout and schematics, okay, they are matching the given functionality, timing, and other specifications. So that is why you do perform DRC and LVS checks. And apart from that, once if you are done with your DRC and LVS checks, you do the parasitic extraction, because till such point of time, okay, before doing the parasitic extraction, you generally will not have the information about the resistance, capacitance, and the inductance values of your layout, okay, very clearly. So then you may ask that, without having these values in hand, how are we going to do the timing analysis? How are we going to do the power analysis and all of that? Remember, when you are doing the schematic simulations and when you are doing the earlier stages layout simulations and everything, all that delay parameter information is coming from your technology library file known as Liberty file. Okay, that Liberty file is a file which is coming from the foundry, right, which is integrated into your electronic design automation tools. And that information comes from a process known as characterization, right? So device characterization is a process from where those parameters are getting generated by the foundries and getting generated by the device physics organizations, okay, who are basically involved in that kind of a work. So basically they do that analysis for different material compositions like CMOS, gallium arsenide, and gallium nitrate, and all those different material composition, and they feed that information in the form of a technology library into the EDA companies and into the fabless companies also. So when the companies integrate that values into the tool flow, you cannot guarantee that the results are 100% accurate. Then what you need to do, once if you actually build your schematic and the layout, and once if you generate your layout, you have to extract your RC values or RLC values, and you need to feed that back into your layout, and you need to feed that back into your schematics, and you need to cross verify whether they are producing the expected response as far as skew, jitter, right, and as well as even rise time and the fall time and everything. So if you have to do that, then you have to extract the values of R, L, and C, that is, right, parasitic, resistance, capacitance, and inductance values. That process, what you call it as parasitic extraction, and the process of feeding those values into your simulator and rerunning your simulations to cross verify the performance of your design, what you call it as back annotation. So once if you do all of this, if your design still meets the specifications, you sign off your design into the fabrication. So now the question is that why we don't follow HDL based design entry, okay, into in the full custom IC design approach. There are no efficient HBLs available yet to model analog blocks owing to inherent characteristics of analog circuits. Remember, if you take a simple even inverter also, CMOS inverter, you have NMOS and PMOS, and in that NMOS and PMOS you have W minimum, L minimum, W maximum, L maximum, such a wide range of values for that given target technology node. And plus you also have your permeability, permittivity, metal oxide thickness, and all of these parameters. So all of these parameters managing with the help of a programming language effectively is very, very challenging. That's why exactly schematic based design entry is even today is the most proven or most preferred approach in full custom IC design flow. Now, moving further, in electronic system design, you have another important step. Okay, this is more on the hardware design, where you once again follow very similar approach what we follow in full custom IC design, where we identify the entire system requirements and we create a bill of materials and we draw the schematic, we add the footprints, okay, right, and we create a net list. And then once we are done with all the schematic simulations, then we go for the PCB simulations, which includes once again placement and arranging of the components and routing the entire board automatically. Once again, here it is automatic placement and routing. Then you generate your vias, okay, right, and you create your PCB layout file, okay, sign off file, which is Gerber, which goes into the PCB fabrication. And once if you get the ready-made PCB, you mount the components which has been selected in the bill of materials, and you basically, right, work on the electrical verification of the entire bare hardware. And then you basically, right, check the electrical interfaces whether they are working properly, and if that check goes successfully without any faults, then your firmware team will mount the device drivers and everything on top of that hardware, and you basically bring up, you make your board alive or else hardware alive, which we call it as board bring up, right? And then the application softwares will be mounted on top of that subsystem, and then you test your entire applications which you would like to run. That is how generally, right, even any motherboard or even your smartphone hardware is going to get tested in a phased manner. Now, coming into full custom and semi-custom IC design flow. Semi-custom IC design flow, as I said, if you want to customize everything to your taste, then the amount of time what you are going to spend is more. So you can see that the design life cycles are longer in full custom IC design flow, and at the same time, the amount of time it takes for a full maturity of the design is much longer. Whereas in case of semi-custom IC design flow, the design life cycles are shorter. Okay, for your information, how quicker the design life cycles are today. If you take any major semicon company today, the design life cycles is less than, okay, right, 12 to 14 weeks. So that is how quicker their design life cycles are today. So coming into the full custom analog IC design flow, okay, right, which is the core essence of this program. In the industry, Cadence gives you the most comprehensive, okay, right, tool sets for your complete full custom IC design flow. Okay, right. For example, if you want to work on your schematics design, you have your Virtuoso schematic editor or composer. And similarly, if you want to work on multi-mode simulation, that means analog and mixed signal designs, okay, you have a simulator known as Spectre. Okay, Spectre is a SPICE simulation engine for you. Then if you want to do the layout analysis, you have Virtuoso layout suite. And if you want to get into the physical verification, which includes DRC and LVS of your layout, you have a tool known as Ashura up to 180 nanometer technology node. But if you are interested in working on 90 nanometer, 45, 28 and lower end technology nodes, okay, right, then you have PVS physical verification system, the tool which is from Cadence. And for the parasitic extraction and the back annotation, you can use Quantus with Spectre simulator again. And for your sign-off checks, okay, you can use Virtuoso. So here you have a comprehensive tool suite which allows you to manage your designs. And apart from that, if you want to create the design entry using your programming approach, okay, right? Cadence has a proprietary technology known as skill programming, with the help of which you can also create your schematic design. That means without drawing the schematics, you can represent your design with the help of skill programming. Plus, if you want to bring in automation as far as your schematic design entry and as well as schematic simulations and layouts, then you can still use skill programming, which is a patented technology from Cadence. Now, this is the more elaborated flow of your custom IC design flow. Remember, custom IC design flow by default, okay, we call it as analog IC design, because generally the standard cells, right, and as well as even the basic analog building blocks like current mirror, voltage mirror, right, and current reference, voltage reference, amplifiers, power supply, all of these blocks are generally built using full custom design approach. So as a result, the approach what we follow here, by default, it is known as analog IC design also, right? So it has an elaborated view, as you can see here. So today in the evening, when we are going to run through the demonstration, we are going to run through a detailed step-by-step orientation for you, okay, further. So because of the interest of time, I'm just holding myself. If you have any questions specifically pertaining to this, you are free to ask those things. We are going to cover very detailed step-by-step procedure of these things in today's demonstration sessions in the evening. Now coming into Virtuoso Schematic Composer tool, it has features like flattening your schematic entry and hierarchy. For example, if you have a complex hierarchy in your design, you can flatten that up, okay, by routing the signals and everything. That is the advantage what it gives you. And hierarchical schematic entry is another approach, okay, right, where you can represent the top level building blocks and start making the connection, and you can flatten that up. And you have a library manager where you can create a component and you can upload it that into your library, and you can keep reusing it any number of times. For example, you can create a inverter, you can create an AND, NOR, or amplifier cells, and you can keep calling those cells, right, to create the instances of that. And you can also do the symbol generation and parameter passing, right, and schematic ERC checks, okay, right, with the help of Virtuoso Schematic Composer tool. And Virtuoso analog design environment, okay, gives you a couple of strong benefits like reuse your test setup. For example, if you have created a test setup, okay, for any of your standard cell, right, or else any of your analog basic building block, then you can reuse that standard test setup either to verify the DC conditions or AC conditions or transfer characteristics, right, according to your requirement, okay, and write simulator for the right job, okay. You can choose the type of the simulation which you want to perform, whether you want to perform DC analysis, AC analysis, parametric analysis, or transfer characteristics. So you choose your simulator for the kind of the simulations what you want to perform. And it also gives you a single waveform window for all styles, okay, right. That is another bigger advantage, and it is a single kernel architecture based also for you. So Virtuoso Spectre simulation gives you all these powerful simulation capabilities. Okay, you are going to see these things, okay, during your lab sessions or else during your demo sessions. So where my team is going to be running through all the details for you. Coming into Virtuoso layout editor, okay, it has a cell layout editor and analog block layout editor, and create and edit layout options also for you, where directly you can start drawing your layouts also, right. And you can also create the P cells, okay, for confining a specific cluster of your design, okay, right, into P cells. So you can do that also, right. And the physical verification, as I mentioned, it includes DRC, design rule checking, and as well as layout versus schematics, LVS, and ERC checks also, right. And all of that can be done with the help of your Ashura and as well as even PVS, physical verification system tool. So as you can notice here, it basically checks for the design polygons, right, and the length and the width and other area of cross sections and the overlap layers, okay, right, everything. So this is the a kind of a basic DRC checks, okay, right, what your EDA tool does for your design. Now the question is that which part of the design flow you want to work with and why. Okay, as a undergraduate student, or else a postgraduate student, or a research scholar, right? Or even a faculty who is pursuing postdoctoral research, right? You may want to choose a specific area, but the question is that which area you want to work with and why. Okay, please be noted that, okay, right, in my experience of 20 years with the industry, what I have noticed is that if you are really logic oriented, you really enjoy programming, okay, then you have better chances of succeeding in VLSI as a front-end design and verification engineer. So where you understand the specifications of the design, you represent that using Verilog or VHDL as a programming language, and you verify the design thoroughly such that you ensure that the design gets killed because of some bugs. So if you have that killer instinct and you can really get into the core of the design, okay, very easily with your logic orientation and with your programming skills, then I would strongly recommend you to pursue your career in design and verification. Whereas as an engineering graduate or else as a research scholar, if you feel that I'm really good at my CMOS fundamentals and electrical and electronic circuit fundamentals, but programming is not something I really enjoy, then no worries. Okay, you can choose physical design and verification where your strengths will really help you to excel. And apart from that, you can also work on circuit design and layouts, okay, right, for the customized design part of it also, subject to condition. If you are really oriented towards the material science and material physics, remember analog circuit design is a artistic job, okay, right? Whatever parameters which you calculate on a paper, and those parameters when you feed it into the electronic design automation tools, it won't give you the kind of results what you expect on a paper. Then why exactly it is? It basically for the reason the tool makes a lot of assumptions, okay, right, based upon the parameters whatever you have fed, which ideally don't even work. So as a result, you need to be keep fine tuning your design by understanding your material physics properties in and out. So if you feel that you belong to such type of a genre, right, then I would recommend you that you should pursue the profile of analog circuit design. Whereas analog layout, okay, it is being treated as a a job, okay, right, which is basically of more of a work uh, laborious job, for the reason there more of your electrical and electronic circuit fundamentals and the your attention to the detail as a layout engineer, that is what really comes into picture. So as a result, today in Indian electronic designs semiconductor design services companies like even Sankalp Semiconductors or even Sankalp HCL today, right, or Karmic, right, and Wipro, and lot of these companies over the last 10 years, the scenario has been changed so badly that, right, they also hire even 10 standard pass outs and even 12 standard pass outs, right, and even basic diploma students, right, and nothing to degrade by the way, right, and they train them on basic geometry of the analog layout and they put them into analog layout analysis. Now the question is that how an engineer can go and compete with them. Remember, the market is wide open for you. So as long as you feel that that is the one area which you can really excel, okay, with your circuit fundamentals also, then you can definitely be a good layout design engineer for the industry. Now, so apart from that, your knowledge about the concepts of physical synthesis, right, and the concepts of DFT, those things also helps you to fetch opportunities in pre and post silicon validation, okay, right, which many of our Indian companies are also working with. For example, Wipro Technologies also works for pre and post silicon validation for their semiconductor clients like Intel and as well as Qualcomm and other companies. And even Qualcomm and other companies, they also work on pre and post silicon validation for their clients, okay. So such type of activities are increasingly happening in our country. Apart from our government defense and development agencies like SCL, okay, where you had a session from earlier resource person, they also work on IC design and fabrication and testing and chip tape out. And as well as BEL, okay, Bharat Electronics Limited, they also work on chip fabrication. But the question is that what kind of a technology node they work on and where the industry ecosystem really lies. Remember, we have the technology nodes today running all the way from 360 nanometer to up to 5 nanometer also. But the question is that which technology node should really entice you more and more? Okay, right? This is one of the uh, uh, piece of information which has been published by Ministry of Electronics and Information Technology, okay, and as well as even Electronic Sector Skill Council of India, that over the years remember, even after 70 years of our independence, we are a service oriented nation. So majority of our income, what we generate, comes from providing services to the clients and the customers of ours who are basically either European or US companies. Now, if that is the case, what really picks us back, okay, right, as far as not having a fabrication unit or not having a IC fabrication units across India. Remember, even if we want to wish to do so, we don't have that IP ownership or product ownership with us. For example, we have already lost the race to, right, Intels and Qualcomms of the world, okay, right, as far as SoC and NoC chipsets. As a result, if you take even your smartphone or else your motherboard of your personal computer or laptop, except the processor and high-speed memories, there are a lot of other chipsets which works at low speed, which works at, right, moderate powers like data converters, sensors, power supplies, right, which work at, which are based on 180 nanometer and 360 nanometer, 90 nanometer and 180 nanometer. So this is something which MIT is been recommending very strongly, that if we have to be self-sufficient in manufacturing at least data converters, sensors, power supply controllers, we should develop IPs so that which can go into the fabrication. And for that reason, in fact, in the last 10 years, SEL is giving the PDK for all the academic network across India, where you can sign up, okay, right? If you're a faculty or research scholar, you can sign up with SEL and SEL will give you the PDK and you can work towards the sign-offs. In fact, just I joined the session couple of minutes earlier, okay, right, when Mr. Jatana from SEL was addressing, okay, and a question came, right, that we want to go for the internship. Honestly speaking, you don't need to run behind internship at SEL. Nothing wrong in you knocking the doors of SEL. But remember, if you go to any industries, okay, in and around West Bengal or else in and around, okay, even Chhattisgarh, okay, right, and Jharkhand, right, where a lot of industries are, right, there, you see that, okay, a lot of those industries, they struggle to, right, get the proper support for the electronics hardware what they use, and at the same time, lot of those chipsets which they buy from either from Delhi NCR shops or else from, right, Pune shops or Bangalore shops, okay, right, getting the support for those things is a big challenge for them, and those things don't make their solutions economical, and as a result, any product which comes out of our ecosystem becomes very costly. How we can reduce that? So you can understand their problems and you can come up with your own hardware architecture, even if you can import the discrete components, chipsets and everything today, but build the hardware for the local, right, applications, maybe a solar panel or else maybe a rural lighting system or else maybe for the right, data network setups of the local, right, gram panchayat, village panchayat. So if you do those kind of things, then next phase can be that where you can understand that what kind of chipsets are going in terms of data converters, sensors and power supplies and other things, start working on those blocks, okay, right, and take those designs into the chip tape out. And at NTUPL, in order to encourage such type of ideas, okay, right, if you visit our website, you see a product known as Vivect. Vivect is a product, we are proud to say that it is being signed off in collaboration with educational, right, academic partner institutions of ours. So if you carry such type of a vision to benefit your local industry clusters and local community, we are happy to assist you further in that direction, in fact. So there is a lot of benefit for you, okay, because MIT and as well as even Niti Aayog is been clearly giving the mandate for the last 15 years that, right, we need to be focused upon, right, manufacturing, right, and product driven economy. So as a result, if we have to really move in that direction, so then we need to support those activities, because that is where exactly our success lies. So the rewards and recognition is very huge for you in that direction. For example, you can help the startups to build such type of solutions, okay, right? And also such type of solutions are highly appreciated and interested by OEMs also, like Intel and as well as Qualcomm, NXP, Continental, and so many other organizations. Apart from that, even in Indian design houses, they are interested in your solutions, and definitely the product majors, they are also interested in you. And test chip solutions, SEL Chandigarh is one option for you if you are intended to work on 180 and 90 nanometer technology nodes. But if in case if you are intended to work on sensors at 45 nanometer and 28 nanometer, no worries, we are happy to help you. We are collaborated with IMEC Belgium, where you can you can give us the details. What is the technology node you are interested in? What is the tape out period which you are looking at? What is the application, and which is the funding channel for your tape out project? Okay, right? And all those details will help you in signing up with signing up with IMEC, and where you can get the PDK, process design kits. Okay, right? And we'll help you to get that integrated into the Cadence tools. And remember, any electronic design automation company, whether it is Cadence, Mentor, or Synopsys, they only give you the dummy kits which can be used for the academic study purposes. But the moment you want to get into product specific R&D activities or chip tape out, you need a design kits, okay, which can help you towards the product sign offs or chip sign offs. So such type of PDKs, right, you get it from Tower Jazz, or else you also get it from companies like Global Foundries, right, TSMC. So if you are interested in signing up with such type of foundries for your R&D work, right, we can help you. And further, we'll also assist you by integrating the tool flow with the PDKs, and so that you can work on those things under NTUPL community initiatives for ASICs and systems. Okay, it's a community project which we drive to strengthen up the local communities and local industries in India. And we are proud to say that we have already done 3 to 4 projects of that nature, okay, right from our end. And you also have a lot of prototype support from the design contests which are driven by semiconductor majors and Indian Electronics and Semiconductor Association also. And now coming into the job opportunities, one of the key questions which students are asking, okay, right, not only during this pandemic period and before also, that where the opportunities lies. Remember, the industry clusters who offer the opportunities for you are a big ecosystem. For example, you have Indian design houses like Wipro, Tech Mahindra, Infosys, Sasken, HCL, Tata Elxsi, Mindtree. All these companies, when they do the campus hiring, please be noted that they also look at the talent who can fit into their product engineering verticals, that is PES, what they call it as. And if you are competent as a VLSI engineer, they don't mind you pulling you out of a IT job and putting you into VLSI job in those organizations. But only thing is that you need to showcase to them that you carry the competency, right, which can fit into their requirements. And similarly, public organizations like BEL, ISRO, CDAC, and BHEL and SCL, even they also hire a lot of engineers every year for their requirements, in fact. Now coming into EDA companies, even companies like Cadence, Mentor, and Synopsys, they don't hire in large numbers, but they hire in the range of around 15 to 50 engineers every year. And same thing is applicable to companies like Xilinx and Analog Devices, Aldec, and Altera, which is Intel PSG today. So all these companies, they hire in big number. Coming into the product companies, for example, Qualcomm, in the last 4 years, right, I have seen every year they hiring 250 to 300 engineers from the engineering institutions. And same thing with even companies like ARM, Microchip, right, and Sony, Motorola, which is NXP. So all of these companies, okay, they are continuously hiring engineering students from the campuses. And coming into the segmentation of the this entire industry, you have something like, right, IDM, pure play and fabless companies. For your information, IDM stands for integrated device manufacturers, who may or may not offer foundry services for you, right? Whereas the pure play companies are the companies who only offer foundry services, like TSMC, right, and Chipmos, Tower Jazz, right, and Faraday's and other labs who basically give the fabrication services to other fabless companies like even, right, Qualcomm. Okay, right. So fabless companies are the one who do not offer any foundry services or fabrication services, but they only provide design services and third party IPs, okay, IPs for the other companies. So coming into analog circuit and layout design engineering, if you want to excel yourself as an engineer in the field of analog circuit and layout, then you need to have proficiency in your analog electrical and electronic circuit fundamentals begin with. Then circuit and layout design methodologies you should be very familiar with, and scripting knowledge, as I mentioned, either Perl or skill scripting or Linux concepts, okay, you need to be familiar with, okay, right, and analog layout concepts for the contemporary designs, okay, what they expect you to be familiar with. So if you have worked on any memory standard cell of reasonably good complexity and good architecture, and if you have worked on any IO controller, okay, chipset architecture, even at 90 nanometer or 180 nanometer, if you have done the things end to end, then that really adds up to your profile, in fact. So coming into Cadence University program, so Cadence University program under its academic network gives electronic design automation tools for the academic institutions across the globe, so that they can build the tomorrow's engineers in their campuses. So that is the sole purpose of Cadence supporting educational institutions to be get that benefit of having the industry standard tools, okay, right, in the campuses. And apart from that, Cadence also gives, right, students who are eligible to participate in their prestigious annual Cadence design contests, and faculty training programs are also available from Cadence. And we are the front face of Cadence as Cadence academic partner, right, and we also provide, right, joint programs, okay, right, and expertise talks, okay, from the resources from NTUPL and as well as from Cadence. And Cadence prefers to source entrants from this program only. Every year the entrants, right, and as well as employment fulfillment of Cadence happens through Cadence University program. And it also helps foundry access through their aggregators like TSMC and as well as global foundries. And a couple of other value added services what Cadence University program offers is the cost access, that is Cadence online support. So if you are working on any Cadence tools and technology, if you need any technical assistance, you can reach out to our team. So we are happy to assist you, right? And rapid action kits, for example, if you are the first timer as far as a specific tool and specific methodology is concerned, there is good number of reference designs and case studies which are built by Cadence and NTUPL, so you can take the benefit of that. And generic PDKs for the educational learning purposes are offered by Cadence. And apart from that, you also have online and offline training bites and custom training programs also, which are made available from Cadence. So with this note, I'll stop at this point. So if you have any questions, you're most welcome. Any questions?
Thank you. Thank you very much, Mr. Damodaran, for your nice presentation talk. So I would like, if is there any queries, anyone can ask Mr. Damodaran.
Yes, thank you, Mr. Damodaran, for your nice and elaborative lecture regarding the different aspects of ASIC design, as well as the model that we will be using, and everything that you have described. It is really nice to know about the what are the status or the state of the art of VLSI techno analog devices, and Cadence tool, why we are using it, and where to use, how to use, and the total flow, how to tackle the flow, and everything is clear. But I think some question till there arises, that regarding that you are telling about the full custom and semi-custom design. Okay.
Yes.
There are some questions not the questions. It is my liking to know that how you are doing so nicely. Actually, the thing is, semi-custom and full custom you are asking about. Semi-custom means we should start with the functional block with
Yes.
modern approach. Yes.
Yes. Yes, madam.
Okay. And if it is full custom, then we should start with the standard cell design
Yes.
and the foundry which
Yes.
are providing,
Yes.
that should be the full custom set.
Yes.
Okay.
Yes.
So in that case, when we are starting a system or designing or maybe fabricating or
Mhm.
maybe assembling, or we are product development for a small
Mhm.
system, say, in our case, it will be low power, maybe low cost. Most important thing is low
Mhm.
cost, low power device, and we should like some kind of sensor acquisition, maybe some kind of that you are telling about DC-DC converter, sometimes some kind of switching or components we require that that should performance is a very nice way like supercapacitor or kind of components that everything. Okay, so now if we now combine to make the system design, so what should be our approach and how do we test that yes, our cost and performance really optimize to give it a product.
Okay, so the approach is, madam, if in case if it is towards having, I mean, is to build a electronic subsystem, okay, for the specific problem, okay, right? Then generally it is good to start with uh, how we can build the smaller chipsets, okay, which are required for that hardware, right? That is the uh, good approach to follow, okay, because that is the approach what even strategic electronics of our country like DRDO labs, they are also following, because each and every chipset which goes into an electronic subsystem cannot be made indigenously ourselves, because then all our projects goes for years together and we may not be able to complete our contemporary requirements. So as a result, there is a two-way approach here where whatever components, okay, that needs to be imported, we continue to need to import for probably another couple of more years. And whatever components, for example, data converters, right, power supply chipsets, right, and sensors, those kind of blocks, we need to identify what type of a signal chain which we are trying to address. It may be for a very generic consumer electronics application, or else it may be for a secured communication application. We never know. So depending upon the application, we need to build a framework, okay, right, specifically for that, and we need to sign up with a foundry, right, and get that PDKs, okay, right, integrated into the tool flow and start building those blocks. For example, if it is a uh, power supply chipset, in that power supply chipset, hardly we may have DC-DC converter or AC-DC converter. So that reference block, voltage reference block, and the regulation block, and those kind of a blocks, an engineering graduate or a PhD research scholar may be able to do it in 9 to 12 months, and with a proper industry sign off. And once he does that, then that work can be sent to the fabrication and get it done, right? And once the fabricated chipset comes, right, probably the next batch of engineers, they can work on pre and post silicon validation, post silicon validation activities, so that it can be a good learning outcome for both for the research scholars and as well as the students. So if we are successful with initial trials, then those chipsets which are being considered as a 100% successful sign-offs, those components can make it into our electronic subsystem. That automatically gives the confidence for the local industry clusters, madam, where they feel that, okay, fine, right, West Bengal Technological University can give such type of solutions for us. Let us go to them rather than going to some, right, design consultation agencies in Pune or in Bangalore or in Hyderabad, in fact. So this is the approach what I have seen institutions in Maharashtra, institutions in Tamil Nadu, institutions in Andhra Pradesh and Telangana, they have adopted. In fact, I myself was involved in one of the institution in Tamil Nadu, PSG Tech, right, which provided this kind of a complete hardware solution for sharp motors, okay, which is point pumps, who export submersible pumps to 140 countries, madam. Okay, and their controller board, it is completely indigenously developed, and even that chipset, okay, which is going into that today, it has been done in India. In fact, in the initial years, they were importing that chipset because that was built on a small CPLD. Originally, this consultation happened more than 12 years back, where they were implementing it on a microcontroller. But every time when there is a new requirement came in from the customer, they were forced to replace the microcontroller with a different series of microcontroller and change the entire hardware. So I recommended their students to replace that entire microcontroller with a small CPLD, and later I asked them that they can make even that, right, a program logic with the help of, right, a customization chipset, okay, right. But they went with in the phase 1 with the CPLD, and just about 4 years back they built their own chipset, okay, right, and today that entire product is run with that activity. And similarly, another institution in the Western Maharashtra region, okay, right, Southwestern Maharashtra region, madam. In fact, all the PCBs which are needed for the sugar mills, it is coming from the Department of Electronics and Communication Engineering. I believe West Bengal also has such type of rich, right, industry clusters. And similarly, right, iron ore industries in Jharkhand and as well as Bihar, which is closer to West Bengal, and even Dhanbad, okay, right, which is part of Jharkhand today, right. So they work on lot of hardware, and if the technological universities and technical universities of West Bengal region can cater to them, I think they don't need to import lot of hardware what they are importing today, madam. In fact, I believe that should be the secret recipe of for our success, according to me, because this is something which I have seen as the success stories from our own community, in fact.
Yes, true. So in that case, we can, our students, participants, and young faculty members, all are doing this, and we really be motivated, and really we feel that if from electronics point of view, and you are telling that physical verification and that kind of things also started with schematics and going to checking and doing the things from different fab lab, it is really a good approach to design the things in a cost-effective manner. Yes, but the thing is, whether they are the fab labs, the foundry, they are really collaborated with the government institution, because we have not so much of fund. Okay, so what to do about the fund?
In fact, madam, PDK access comes to you at free of cost. Okay, for example, if you want to go for a test chip tape out of 180 or 90 nanometer, madam, okay, right, it won't cost you much, okay, right, it will be in the range of 3 to 5 lakhs only. What you can do is that you can even invite a cluster of institutions to join hands, so that each and every institution can work on one small block and integrate that, and even the cost can be shared, and that can be taken into the foundry, okay. And SCL gives that chipset also, right, 5 samples of the chipset at 0 cost, as long as it is a community backed project, in fact. Whereas
Community back. So we have to write a community back, or kind of support of MSME, or kind of who they are using some type of controller. Once we have made a industry academia conclave, and we have seen that they really need some electronics controller or kind of automation kind of thing, but they really require this kind of microcontroller.
Yes, not only controllers, madam, even it can be a small sensor, or else even it can be a small power regulator or power supply.
Yes. Even solar industry require that kind of DC converter and switching and that kind of things also. And one important thing, some sensors we are thinking in solar industry or solar thermal, they are so costly, pyranometer and pyroheliometer, and their circuitry. So why not we are making it in India, so that the cost may be reduced within a small tens of 100 or like that.
Yes,
okay.
Absolutely.
So that can be possible, I think. So in near future, if the students are interested, because really India needs to have some kind of this design engineer with a proper system design to support the society and to make their skill developed and serve to the community. Okay.
Now, once the students work on these things, madam, automatically industry will run behind them rather than they running behind the industries.
Yes, yes, that's true also. Okay, thank you. And I think the things that we are maybe we are not make up almost the things that you have discussed. But if there is any loopholes that, and then we will be discussing it in the demonstration or the hands-on workshop session. And any faculty member, students, you have questions? So I have one question, that if the functional block, then why we are starting with RTL, not the block of function?
Okay, it is basically that any design, okay, right, will not be as simple as the small functional blocks, madam. Okay, for example, if you take a processor, or else if you take even the small memory controller, for example, the memory controller of today's in motherboards, they are very complex. For example, DDR2, DDR3, or LPDDR, okay, right, they follow a lot of memory segmentation and right memory buffering and all that, okay, right, so which is a very, very complex thing. So if we start implementing such a complex logic with the help of standard cells, then which is like I'm implementing a complex logic with the help of my structural design implementation approach, which is going to be tedious. Rather than that, what I do is first I verify that whether that memory read operations, memory write operations with proper latency and proper performance, can that be done with the help of a behavioral modeling. So that is what industries they do. They start with a behavioral modeling of the code and check that whether the desired functionality can be achieved first. And once they do that, then that code will be converted into HDL, and then they go for the hardware check. Okay, that sometimes many a times they do that with the help of FPGAs. They implement that design on the FPGAs, and on the FPGA development boards, they try to see that how the memory read time and write time by probing the signals with the help of logic analyzers and as well as pattern generators. But once they do that, then they have to go for a chip tape out. In such cases, the entire design life cycle, if they go with the functional block approach step by step, then the design life cycles will be more than 12 to 15 months. Definitely companies like Rambus or Micron, or Samsung may not be interested in 15 to 18 months of design life cycles today, because they want to compete with their competitors also, right? So that's the reason they follow that approach.
Thank you. Thank you once again. Any questions? Okay. Thank you once again. And hope we will be meeting again in the workshop or session, or maybe in the next session or the day after, day tomorrow. The tomorrow you have the session. Yes.
Yes.
Okay. Then,
okay, all the very
now,
best to your team. Okay, right. And
thank
I
you.
wish a productive learning outcome, okay, for all the participants.
Yes. And hope we will be collaborating to develop something for the society. Thank you.
Look forward to working with your team. Thank you. Thanks for that.
Thank you.
All the very best to all the participants.
Yes. So now we may have some half an hour lunch session. After that, we'll be coming back by definitely by 3. Okay. Now we'll be closing the session. Shobik or Mihir?
Yeah.
Yes,
So, Prem will close the session. I think we will start from 3 p.m. onwards. The hands-on session will start by 3 p.m. and so that's it.
Yes. Thank you so much. So we now, all the participants, now you have the session. After that, we will be coming back by 3, definitely. Thank you.
Hello.
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 Yeah,
Yes,
Prem.
ma'am. The system will be on. And the participants are requested to kindly rejoin in this link only.
Okay. Thank you.
Okay.
The system will be on. Yes.
Okay. Thank you.
Yes, ma'am.
Okay.